I will be starting in a minute or so.
The following message is best viewed on an oscilloscope. Okay, so I think we will start the session. So let me welcome everyone to the first Astro-particle Physics and Cosmology session of ICHEP 2020. So thank you all for joining, and thanks already in advance to all the speakers for their talks. Just a few things. So we have 9 talks today. It's 3 talks, then a half-an-hour break, then 3 talks, half-an-hour break, and 3 talks to follow. And at the very end of the session, we reserved 1 hour of discussion for all the talks of the day, whoever wants to join. Also, please, please make sure you use the Mattermost link if you want to have private chats. Also, you can post your own Zoom channel there if you want to have private chats with other participants on your research. If you need to, so all the talks are 25 minutes, so 20 minutes plus 5 minutes questions. So if you need to ask any questions at the end, please click raise hand, and then there is you'll be ordered in a waiting list, and I will be giving you I will be letting you ask your question. So I think that's all for the introduction. I think so. The first talk of the day is Elaine Fortes. So Elaine, can we see you and your slides, please? Okay. Can you share your screen? We don't hear you. Let me unmute you. Can you unmute your microphone, please? Okay.
Are you listening to me now?
Yes, great. Okay.
Okay. So my talk is dark matter annihilation in the most luminous and the most massive ultracompact dwarf galaxy, UCD. This work was done in collaboration with Osvaldo Miranda, Floyd Staker, and Carlos Wunsch. This talk is based in this archive. So we know that the universe composition, and we know that dark matter accounts for around 93% of matter in the universe. Its presence could be inferred from many astrophysical observations, and its gravitational effects can't be explained by the accepted theory of gravity. So, due to the importance of this subject, we're going to model dark matter content in ultracompact dwarf galaxies. So, ultracompact dwarf galaxies are dense stellar systems, brighter, larger than globular clusters with a mass greater than 2 million solar masses and radii greater than 10 parsec. They exhibit properties such as mass, luminosity, size, and these properties challenge the conventional understanding of them in comparison to canonical stellar systems. We have that the nature, origin, formation, and dynamical evolution are intensively studied. In fact, the discovery of UCDs, since it discovers many attempts of observation and theoretical simulations were done in order to shed light into their origin. Interpretations suggest that UCDs as results of the evolution of primordial density fluctuations or formed through mergers of globular clusters. UCD can also be placed as remnant nucleus of larger galaxies, remnant star clusters, and massive globular clusters. They are also dubbed as dwarf globular transition objects and attempted to express their origin, which is uncertain. So we are going to study two important dwarf galaxies in Virgo and Fornax cluster. We are going to model dark matter presence in this ultracompact dwarf galaxy. And so we are going to study Fornax UCD3 and M59 UCD3. On one hand, Fornax is the most luminous UCD, and M59 UCD3 is the most massive UCD. They have similar distance from Earth. Fornax UCD3 is 20.9 megaparsec, and M59 UCD3 is 14.9 megaparsec. Recently, it was discovered a supermassive black hole in Fornax UCD3 with around 3.5 million solar masses. And it's possible that there is a supermassive black hole also in M59 UCD3 with a mass around 5.2 million solar masses. So could there be dark matter in these UCDs? We are going to model the presence of dark matter through enhanced dark matter profiles, considering the existence of dark matter and the supermassive black hole in these UCDs. In this magnifying, you can see an image of Fornax UCD3 and M59 UCD3. And in this table, you can see some characteristics of this UCD galaxy as distance, the possible age of the black holes, the mass of the black holes, the stellar velocity dispersion in this line here, and the radial extension, and the M/L ratio, which is increased in comparison to conventional stellar systems. In order to model dark matter in these UCDs, we are going to consider that dark matter is responsible for 8% and 32% of the fraction of mass in these UCDs. The fraction 32% is claimed to be compatible at 1 sigma level with the observed velocity dispersion profile. So we are trying to model dark matter considering especially the radial flux that can be produced through dark matter annihilation. We have dark matter going to find some final states, and this will produce some synchrotron flux, some radial flux, which can be measured. And if we have experimental limits, we can have some parameters and we can adjust them to see how the dark matter component behaves in this case. In order to calculate the radial flux, basically we need to solve the diffusion and energy loss contribution equation. Here we have the source term. Here we have the loss term, the B loss term. And here this term is responsible for special diffusion. When we have a situation that the electrons loss energy in a scale shorter than the special diffusion, this term can be neglected, and this equation can be simplified to this form. Look at this form. We have the annihilation cross-section, we have the dark matter density here, we have the mass of dark matter, and we have the loss term here, B loss. And the loss term takes into account some loss due to synchrotron process, inverse Compton, Bremsstrahlung, and Coulomb interactions. And here we have the key, the source term, which relates the sigma V, the density of dark matter, and the spectra produced by the final state particles. So we are going to work with these equations to have our flux. And now we are going to pay attention in the density that are going to be considered here. We have a canonical density, which means the Navarro-Frank-White profiled. This density was built in order to fit the special mass distribution of dark matter, but it was fitted by N-bar simulations. This distribution doesn't take into account the black hole. And now we are going to see other spike distributions that take into account the black hole presence in these UCDs. For example, now we have the Navarro-Frank-White plus spike profile. Spike means a higher concentration of dark matter. We see that in opposition to the Navarro-Frank-White here, we have a profile divided in 3 regions. One region is far from the radio of influence of the black hole. The other region is between the saturation radio and the radio of influence of the black hole. And the other region is less than the saturation radio. Here, the sat means that rho-sat means the mass of the black hole divided by the age of the black hole and the annihilation cross-sections. And we have another spike profile. Here we have the mini spike, which is different from the spike profile. We also have 3 regions, but we work, when we are in a region which is smaller than the Schwarzschild radius, we have a density that is null. In the second region here, we have a saturation density, which is expressed between the Schwarzschild radio and the saturation radio. In the third region, we have another density, which is expression in the region between the saturation radio and the radio of the influence of the spike. The radio of influence of the spike is expressed by the gravitational constants, the mass of the black hole, and the stellar velocity dispersion. And for the last profile, the last spike profile, we have the spike, the pure spike profile, which can be expressed also according to 3 regions. One is null, is an example of the last slide presented, and the other 2 regions are between the Schwarzschild radio and the radio of influence of the black hole here. And the second is far from the radio of influence of the black hole. So we are going to compare the canonical Navarro-Frank-White profile with these 3 spike profiles and see how does the density of dark matter behaves in this case. Here we have the result of our simulations. We have in the horizontal line the distance, and the vertical line we have the density. In the left panel we have the M59 UCD3. In the right panel we have Fornax UCD3. Here in this line we have Navarro-Frank-White. Here we have Navarro-Frank-White also, and the other 3 lines are the spike profiles. We see that we have an annihilation plateau. What does that mean? This is a constant line here, right? And in this case, the dark matter density becomes so high that the annihilation depletes the number of particles. And this situation produces a plateau. And this red line, it was just a Frank profile, which was used in the beginning to adjust, to mimic the dark matter composition in these UCDs. And now we are going to see how these profiles enhance the radial flux for dark matter. In order to perform these calculations, you used a magnetic field of 7 microgauss and a gas density of 10 to minus 4 centimeters to minus 3. In the left panel, we have, again, M59 UCD3. In the right panel, we have Fornax UCD3. The horizontal line is the frequency, and the vertical line is the flux. And this black line is the 3 sigma upper limit obtained by M59 UCD3. In the absence of constraints for Fornax, we use this upper limit to constrain its results also, due to the similarity between these two UCDs. In these two lines, the red one and the orange one, here and here, we have the Frank profile, which was the first one used to simulate the Fornax cluster and to mimic dark matter composition. The other upper 4 lines denotes the spike profiles. Here we work with the BB bar channel. Dark matters go to BB bar and has a mass of 34 GeV. In this other slide, we work with dark matter of 10 GeV, which annihilates in mu plus, mu minus. Again, we have the Frank profile here, and here we have, again, the Frank profile. We have in the left side the M59 UCD3, and at the right side, we have Fornax UCD3. And again, we have the 3 sigma upper limit for this flux and 3 sigma upper limits for these fluxes. And what we can see from these graphics, when we're trying to use spike profiles, we have to pay the price of decrease the annihilation cross-sections by many orders of magnitude compared to the thermal cross-sections. So what can we conclude? The size of the spike and the internal properties of the black hole, which is in the UCD, can leave their imprints in the synchrotron flux, in the radial flux. And this imprint is very strong if compared to this one predicted for Fornax simulations as the Frank profile that I told you. The dark matter density distribution that mimics dark matter in Fornax, which is the Frank profile, produces radial flux well below the upper limits predicted for M59, and for Fornax, we see UCD3. And when we work with the BB bar, we consider that the cross-section used to simulate Fornax and M59 UCD3 is 10 to minus 26. And when we work with mu plus mu minus, the sigma V is of order of 10 to minus 28 centimeters cubic per second. And considering the set of parameters studied here, we conclude that the Navarro-Frank White plus spike and the pure spike profiles are the profiles that most empower the flux. And as a consequence of that, the annihilation cross-section should be decreased by many orders of magnitude in comparison to the thermal cross-section to agree with the upper limits for these UCDs. In the absence of gamma-ray signals, synchrotron emission is an interesting proof for testing the potential astrophysical signature of dark matter. Thank you very much.
Okay, thank you very much. We have a few minutes for questions. Anyone who wants to ask a question, please raise a hand. So I have a question. So have you thought of trying other types of profiles? Or is NFW well motivated for these systems?
We had tried also a Nasto, Moore, isothermal, a Burkett, but since we were working with black holes, we just considered the Navarro as the canonical profile and just put some other profiles that depended on black hole masses, black hole age, black hole signature, dark matter mass, this kind of stuff.
So and then the spike, there are some models which can produce this kind of behavior. Or is it a phenomenological way of testing such a density?
Sorry, I didn't understand the question.
Yeah. So are there other? It looks that you have this spike on top of the Navarro-Frank-White profile. Are there any simulations which show that this is produced? Are there any models which produce the spike?
The spike profiles were very well studied in the supermassive black hole Sagittarius A. And what you can have is constraints from radio flux or for gamma ray flux, when you can put some spike profile and you can set limits in the annihilation cross sections or in the dark matter cross sections for the spikes that we are going to consider. Some of them have the power of increasing more the flux than the other ones. This is what I can say.
Okay, thank you.
You are welcome.
Questions? Okay, so let's thank Elaine again for the nice talk. It looks like our next speaker has not joined us, has not responded to my email. So is it possible to move to the next one for the time being? So Fernando, will you be able to speak next?
Yeah, sure, no problem.
Okay.
Hi.
Okay, hi. So whenever you're ready.
Yeah, let me share my screen. Hey, can you see it?
Yes, it's all there.
Okay, so thank you, and thanks also to the organizers for giving me the opportunity to present this work here. So I'm Fernando Arias Aragón, and I would like to present this work that we did on the production of thermal axions across the ElectroWeak phase transition. And this presentation is based on one paper which is already out on the archive, and it was done in collaboration with Francesco D'Eramo, with Luca Merlo, my supervisor, Alessio Notari, and also Ricardo Tambuja Ferreira. But it's also based on some other work that will be appearing hopefully next month or in the next 2 months at most. Okay, so first, let me give you just a short summary of what this presentation is going to be about. So at first, I would like to convince you that what we're looking at is something interesting, and it's something that may shed light on many things. And then I will give you some details on how the computations were done, what type of processes we consider to produce these axions. And then I will move on to the results, going first for a model-independent approach. And I will discuss a bit more later what I mean by this model-independent approach. And then I will talk about 3 UV-complete models. 2 of them are very well-known examples of the invisible QCD axions. And then another model that we consider interesting because it's related to flavor. And then last but not least, I will comment on the complementarity that this observable that we are going to study has with the xenon 1-ton excess, which is something that everyone is talking about today, nowadays. So it's something exciting to see. And finally, I will just leave you with some general remarks of all the things that I said through the presentation. Okay, so first thing first, why do we want to think about axions, right? So when you look at any theory beyond the standard model, it's really common that you find new light degrees of freedom that appear there. And in particular, axions are a very well motivated hypothetical particle. First, because it was proposed to solve this strong CP problem, right? Which is a huge fine-tuning problem that the standard model has of why this dimensionless parameter has to be smaller than 10 to the minus 10, which is super small. But then it was also found that axions can be a really good dark matter candidate. So by the price of introducing one new particle to solve one theoretical problem, you find that you can also solve this long-standing issue of what is dark matter in a universe, right? And we also have a more theoretical reason to want to consider axions, and it's the fact that they arise naturally when you consider many string theories. So it's not uncommon to think of them. And finally, the collaboration xenon 1-ton measured this excess not too long ago. And one of the possible explanations to this excess is that there is a solar axion. So nowadays, right now, is a very interesting time for us who are looking for axions. And speaking of looking for axions, there are many ways in which you can search for them. So you have, for example, helioscopes or haloscopes, like let's say CAST, DIAXO, or ADMX. But you also have lab experiments like the light shining through wall experiments. And we also have, of course, dark matter recoil experiments like xenon 1-ton. But apart from these direct searches, you can also see the effect of having an axion through indirect things like looking at stellar cooling and stellar evolution, where axions may have an impact. However, we wanted to go in a different direction that is not either the direct searches or these stellar observables. So we wanted to consider the possibility of looking for the axion with a cosmic probe. And the cosmic probe, the observable that we consider, is the effective number of neutrinos, right? So if you have a relativistic relic in your universe, it will leave an imprint on the polarization of the CMB, and this is something that can be parameterized using the effective number of neutrinos. And you can show that it can be transformed essentially into the amount of axions that you have at the early universe. So this is an interesting observable, first because it's going to be probed early in the future by the CMB Stage 4 collaboration and also LIGHTBIRD and the Simons Observatory. But it's also interesting because the effect that your axion has on delta N effective is going to depend on the axion couplings to the rest of your particles, but also on the axion decay constant. So it's going to be something specific related to the nature of your axion. Now, to give you just a rough idea of what types of processes we consider, here you can see the typical generic Lagrangian of the axion interaction with any particle in the standard model. So essentially, you have here the anomalous coupling of the axion to gauge bosons. And you also have the typical derivative coupling of the axion to fermions, where you can consider here any particle of the standard model. Now, for the processes that we consider, we can divide them in three classes of processes. So first of all, you have processes where the axion only interacts with gauge bosons, only gauge bosons involved. Then you can also have fermion gauge boson scatterings that produce an axion. And you finally can look at processes where your fermion interacts with one part of the Higgs doublet. And as you will see later on, these three processes have characteristics of their own that make them worthy to be studied separately. And finally, this is something just trivial to say that the production of axion is going to be most efficient when the production rate gamma exceeds the value of the Hubble parameter. And since we are considering the axion production in early universe, we will be in radiation-dominated era. We can assume that H grows with T squared. Now, let's look first at the processes where only gauge bosons are involved. So the first thing to say is that these processes can exist both below and above the electroweak phase transition. And you can see that the production rate is roughly going to be proportional to the cube of the gauge coupling constant and to T cube. This is important. Why? Because as you have the cube of the gauge coupling constant, the most relevant contribution is going to be the one given by gluons, because they have the largest gauge coupling constant. And since you have a T cube dependence, when you find gamma over H, it's still going to be something that grows with T. So these type of processes are going to be very relevant, especially at high temperatures, where you may achieve axion thermalization, and then you may have this typical effect on delta N effective, which is 0.027, which is essentially related to the axion equilibrium abundance at very high temperatures, right? And here you can see just an example of the diagrams where the axion can be produced. Now, when we go to fermion gauge bosons scatterings or fermion-antifermion annihilation, these type of processes only exist below the electroweak phase transition. In particular, when you are considering temperatures which are below the mass of the fermion, you will be Boltzmann suppressed. So you want to consider temperatures which are above that mass. And you can see that for that case, the production rate goes with the square of the mass. So when you get to the point of electroweak symmetry breaking, all fermions become massless, and therefore these channels disappear, right? And there's also another big difference with the one before, and it's the fact that it goes with T, not with T cube. So gamma over H is going to be decreasing with the temperature. All in all, this means that the most relevant contribution will be given by gluons, again, because we have this gauge coupling constant, and by the heavier fermions because of the dependence on the mass. And of course, gamma over H is going to peak at around the temperature which is close to the fermion mass. Here, you have some examples of production via top and via bottom quarks. And finally, another very interesting class of processes is the one where you consider that the fermion is scattering with one of the 4 real components of the Higgs doublet. So when you are above the electroweak phase transition, these 4 components can be either the Higgs doublet, the physical Higgs, H, or any of its 3 Goldstone bosons. And when you go below the electroweak phase transition, you have the physical Higgs, H, and those Goldstone bosons are eaten by the gauge boson. So you have the longitudinal components of the W and the Z bosons, right? These processes also will be Boltzmann suppressed for temperatures below the fermion mass. However, the production rate does not depend on the square of the mass, but on the square of the Yukawa. So these processes do not die when you get to the electroweak phase transition, so they can still exist above, and they grow with TQ. So these are also another different type of processes that are relevant at high T, like the gluonic ones. And again, we have that heavier fermion dominates because of the dependence on the Yukawa. And you can see that there are many, many channels of these type of processes to produce the axion. And this was all words, but here you have a graphic summary of what I say. So the red and the blue lines correspond to bottom and top quark scattering with gluons, respectively. And you can see that indeed they die at the point of electroweak phase transition. And then you have the other 4 processes. The pink line is the gluon one, which grows with the temperature, and also does the Higgs one, which is the yellow one, and the Z and W, which are the purple and gray lines. And you can see here that they are dashed just to be specific and say that we refer to the processes with the Goldstone bosons. Now, moving on to the results. The first thing that I wanted to show is we wanted to give an idea of if someone tries to look for an axion through an effective, they may want to consider, okay, what happens if my axion couples to this specific particle, right? So in this period, we followed an operator by operator analysis. So we assume that the axion couples to only one particle, and then we solve the Boltzmann equation considering all processes that involve this specific coupling, and then we find a result that is delta N effective as a function of F, the axion decay constant. There is one small detail, which is that we have to stop solving the equation at 1 GeV because we want to keep all the computations perturbative, right? So if we went to lower temperatures, then alpha strong would blow up. We don't want that. And then you will need to consider production via pions and so on. And that is something beyond the scope of this work. And finally, there is also something really interesting, and it's the fact that the result that you get depends on the specific conditions of the early universe that you assume. Namely, you need to assume one specific initial axion abundance. So you can consider, for example, either 0 initial axion abundance or a thermal one. And in the case where you consider 0 initial axion abundance, you also have a dependence on the reheating temperature because of the processes that grow endlessly with the temperature. Now, here is, this is a detailed plot about each specific process, the contribution that each process is giving to delta N effective. For example, these blue lines, the yellow, purple, and gray lines, they are all associated to the axion top coupling, right? So what you should look at is actually the black line, which is what you obtain when you solve the Boltzmann equation, summing all of the processes that involve CT, which is the axion top coupling. And here you have that specific result. You see the blue line, which is the case where the axion couples only to the top, the red line only to the bottom, and the pink line only to gluons. Let me say that these solid lines have been obtained assuming an initial 0 axion abundance, whereas the dashed line is what you obtain when you assume that it's an the thermal axion abundance as an initial condition. And you can see that they go to the typical 0.027 effect on delta N effective. Now, why is this observable something interesting? You can see that going beyond the region ruled out by CAST, there is still some window where the effect could be seen even at a 2 sigma level by the CMB stage 4 experiment. And also it's something really nice to look at because, for example, if you had an initial 0 axion abundance and you measure delta N effective at an axion scale, let's say 10 to the 10 GeV, then you know for sure that it cannot be something that only couples to the bottom. So my point here is that if you had enough precision, and this is really important, when measuring delta N effective, you may be able to disentangle what types of coupling this axion has, right? But this is indeed assuming that you have a huge precision when measuring, so this is something for the future. Okay, so moving now to the UV complete models. If you want more details on the model, just ask me when I finish, but I couldn't fit everything in the presentation, but I have extra slides. So the nice thing of looking at a specific model is that you know the axion couplings to the fermions, so then you can get one exact prediction for delta N effective with some caveats. And the first two scenarios that we analyzed were the most well-known invisible axion scenarios, which are not exactly models because they still have some freedom. So the first one is the DFSZ, where the axion does couple to standard model fermions, and the couplings must satisfy that the up plus down couplings must add up to 1. And there is also the thing that you have two possible values for the E/N ratio, depending on something else. The other one is the KSVZ type of models, where the axion does not couple to standard model fermions, only two gluons. And then you also have a really wide range of values for E/N. And finally, we also wanted to consider flavor axion models, which is something that nowadays is becoming interesting to try to look for axion also in flavor physics. And this is the so-called minimal flavor violating axion, which is some work that I did in collaboration with my supervisor. And it has the peculiarity that it doesn't couple to the top. And it has a sharp prediction for the E/N ratio to be 8/3. Now, here are the results for the three set of models and specific model that I said before. You can see that the KSVZ and the minimal flavor violating axion prediction are really similar to each other because neither of them couple to the top. And this small bump that you see on the minimal flavor violating axion model is due to the axion bottom coupling, which is not present in the KSVZ. But the huge difference is that there is a really large region of the parameter space in the KSVZ that could be ruled out which is indeed not ruled out in the minimal flavor variety in axion, right? So, okay, yeah, if you measured delta N effective at around 10 to the 8 GeV for the axion scale with a huge precision, then you could tell these two models apart. But anyway, if you measure something around here, then you know that there are a wide range of KSVZ-like axions that are going to be ruled out because of cast. And for the DFSZ model, you can see that this is way different because you may also have a coupling to the top, right? So the blue line is considering CT equals 1 and therefore CT equals 0. Then the red line is the opposite, and the black line is an intermediate case where you can see that the axion couples both to top and bottom with 0.5 strength. And you can see that at the moment that you couple to the top, you have an effect on delta N effective at large scales for the axion. So again, measuring with enough precision could help you if for some reason you know that you are looking for a DFSZ-like axion. If you measure N effective with a large precision, then you can tell these different models apart. And finally, last but not least, the very interesting issue with xenon 1 ton. So as you all probably know, xenon 1 ton has measured excess. And one of the many possible explanations is that we have indeed a solar axion. If there is such a solar axion, it could leave also an imprint on an effective. So looking for an effective could be a complementary probe trying to disentangle if this is indeed a solar axion. And what we did in this work, which is already published, was to look for the window of the axion scale that is given by the axion electron coupling wanted by the xenon 1 ton experiment. And we did this in 3 different scenarios. So the first one was considering, okay, let's assume that we have a non-anomalous.
3 minutes.
Okay, cool, I'm finished.
Yeah.
Thank you.
Yeah.
So let's think that we have a non-anomalous cell, right? So it doesn't couple to gauge bosons, only 2 fermions, and we assume all the couplings to be 1. Then we assume something different, which is only coupling to 1 fermion, and then the rest of them at 3 levels, sorry, and the rest of them are generated at a loop level, and finally the DFSZ axiom, right? So here is the result that you find for the democratic case. So the main contribution in this window are due to quark gluon scattering, and you can see that the black line, which is the total contribution that you need to look at, is around 0.045. So it's again within the 2 sigma window. So it's something really nice if the excess is confirmed to be an axion. Now, if you go to the loop-induced case, here you can see that the case where you only have top coupling at 3 level or bottom at 3 level, and either case, if it does couple with strength 10, 1, or 0.1, you can see that in the window interesting for xenon 1 ton, the prediction is again 0.045. So it's more or less the same. Here you have couplings to the charm at 3 level, again 0.045. But it's also really interesting to consider coupling to the tau at 3 level, where the prediction for delta N effective is way larger. It's around 0.3, which can be detected at a many sigma level actually by the CMB stage 4 experiment. And finally, the DFSZ with the 3 possible scenarios that I described before, again gives a prediction of around 0.045. So it's something good to look at for a 2 sigma detection. And that's all. Just I hope I convince you that looking for axions with a cosmological probe is something really interesting and complementary to many other searches, and something that can shed some light on the conditions of the early universe. And also nowadays, something good try to prove whether the xenon 1 ton experiment was indeed an axion or not. So that's all. Thank you for your attention.
Thank you very much. We have some time for questions. Any questions? Yes, Elaine, you can unmute.
Yes. Is there some astrophysics effects that can be explained by axion-particle? Some excess in the fluxes, some kind of that?
At least not that I know right now. Actually, what you have is quite the opposite. You have some bounds that astrophysics set on the region where your axion can live. And this is something really, really important precisely for the axion explanation of the xenon 1 ton excess, right? So I didn't say that I should have. This excess explained by a solar axion is in quite a large tension with the bounds coming from stellar cooling and stellar evolution. So that is something up to other people to try and explore whether there is something that can explain why stellar cooling looks to point in a different direction of the axion-electron coupling and the axion scale with respect to the xenon 110 excess. But anomalies, stellar anomalies, not that I know for now at least. It would be really interesting, really. Thank you for your question.
Thank you. Thank you.
Thank you. Any other questions? I have a question. So is it possible to somehow change the spectral distortions in the CMB by certain interactions of these axions, or is it too naive?
That is a good question. I honestly don't know. We only consider this polarization, which is measured by the N-effective. So you mean something like the tensor to scalar ratio and things like that?
Well, causing spectral, if there is some coupling and there is some energy injection into the CMB, essentially, yeah. But it's okay.
I honestly don't know, but that will be something to look at, yes. Thank you.
And for the, when you say polarization, do you mean the rotation of E into B modes or something
I think
else?
so. I don't really know the details of how it's precisely measured and effective through the CDM, but yeah, I think so.
Okay. Thank you.
Thank you.
Any other questions? Okay, so thank you very much, Fernando. So we'll move to the next speaker. So we're going to skip to the speaker after the break, Sovan Sau. You need to unmute. Okay.
Can
yes,
you hear me?
we hear you. You need to share your slides.
Okay. Is it visible now?
Yes.
Okay, fine.
Okay, good. Okay, so you can start.
Thank you. So, good afternoon, everyone. So, I am Sovan Sau. Currently, I am pursuing my PhD in University of Hyderabad, India. So, I would like to thank ICHEP for giving me this opportunity to talk about my work. So, today I am going to talk about generation of magnetic fields in cosmic string waves. So, this has been published last year. So, this is my brief outline. So, I will first talk about cosmic string, then waves due to cosmic string, and then I will talk about the neutrino motion, and gradually I will propose an idea of magnetic field generation in the cosmic string wave. And at the very end, I will try to calculate a brief estimation of our magnetic field order. So a fundamental unanswered question was that about how in the early universe the magnetic field is generated. This specifically this primordial magnetic field. So generally the value of those primordial magnetic field are small, but that can be magnified later. So there is no exact reason, like there is no exact reason that we can rely on. So here we are trying to propose one simple methodology through which we can generate is seed magnetic field in our early universe. So neutrinos rotating around abalenic string generate a neutral current close to the string. So this neutron current density depends on the distance from the cosmic string core, and this neutron current density will form a gradient in the plasma. And this neutron gradient as well as the electron gradient also present in the plasma will generate a neutral current. And this neutral current gradually generate a cross perturbation in that cosmic string wave, and this cross perturbation will help to generate a magnetic field in the cosmic string wave. So now I will start with the cosmic string thing. So what is cosmic string? Cosmic strings are 1D topological defect that is formed due to axial or cylindrical symmetry breaking. So if we try to talk mathematically, so it is a solution of some underlying field theory, and basically it's a infinite filament of energy. So is by nature we can take it as a cylindrical thing. So we will do everything in cylindrical space time. First, this cosmic string was proposed by Tom Cable. So here in the picture, what we are seeing, this green thing is our cosmic string, and cosmic string space time is conical. So that is drawn beside this cosmic string image. So underlying field theory that we have used for our work is Abelian-Higgs model. So, and Abelian-Higgs Lagrangian has a string-like solution. That string is Abelian-Higgs string. So basically, we are working with Abelian-Higgs string. And in some previous work, we have seen that if we distribute some massive particle in the plasma around this Abelian-Higgs string, after some time, those massive particles will rearrange themselves and they will make a cluster around the cosmic string. And not all of the massive particle will form a cluster. Just for specific set of linear momentum, angular momentum value of those massive particles, they will form cluster closed orbit near about the cosmic string. So we'll use this property for our case. So this thing is analyzed in for static cosmic string, but we'll do the thing for our moving cosmic string case. So now I will talk about the cosmic string wake. So whatever phenomena we are going to discuss, everything will be happening in the cosmic string wake. So now I'll tell you how this cosmic string wake can be formed. So when a string is moving in the plasma, so suppose if it is moving in some direction, so it will swept out some surface area behind the string. So and so what will happen behind the string? Initially there will be a deficiency of matter. So from the background, so background matter will try to go to fill this vacancy. So this matter accretion will form a 2D structure that is called cosmic string wake. So generally this wake, as this cosmic string space time is conical, so this due to this conical nature, this cosmic string wake structure will form. So here in the picture, we are seeing that cosmic string is that black dot is a cosmic string moving in the right direction. So in the behind of the string, there is a wake is forming, and particles due to this conical nature of space time. So matter is converging in that wake region. Okay. So if the string has a velocity of vs and the deficit angle of the string is del theta, so we can calculate a velocity key, that is this small delta v, which is equal to 4 pi g mu vs gamma. Gamma is the relativistic factor. So what this velocity key we use for? So this velocity key will help to move this massive particle in the wake region. So due to this velocity kick, so this massive particle will converge to that wake regions. So there will be, after some time in the wake region, we'll see an over density of particle there. Okay. So now we'll analyze the motion of particle in that wake. So we have taken neutrino as our massive particle. So we'll analyze the motion of neutrino. So I have told previously that for specific set of energy, momentum, and angular momentum values, they will form closed orbit near about. So we have taken this set of value, that E energy is 1.083, linear momentum is 0.025, angular momentum 0.02. So there is no unit because all the units are dimensionless now. It is divided by mu square. So for neutrino, we are solving covariant Dirac equation. Okay, so we will be solving this covariant Dirac equation in cylindrical spacetime, because we are analyzing the cosmic string around cosmic string. So we are using a cylindrical metric. It is the generalized cylindrical metric we have taken. After solving the Dirac equation in this spacetime, we are getting this wave functional form. So as you can see, there is a beta there in the wave function. So this beta stands for it has two values, +1 or -1. So we have started talking about neutrino. So we can do the same calculation for antineutrino also. So if we take neutrino, then this beta value will be 1, and if we take antineutrino, this beta value will be -1. Okay, now we have to calculate the current because we want to analyze the motion of the neutrino. So as neutrino has no charge, so definitely this current will be neutral current. So neutral current means it will be related to density of the neutrino in some place. So this small j is the neutrino current density along z direction, and in the capital J is the total neutral current. So we have integrate the small j over whole space, and we have integrate this function in with the help of mathematics, and then we have plotted with respect to here you can see that in the plot there is a j across along y axis, and along x axis it is alpha. So from the plot we can see that our current is oscillatory in nature, and it is with the increase of distance from the cosmic string, it is gradually decreasing. So there is two positive peaks are there, negative peaks are also there. So from this plot, so far we can tell that for the positive peak, there is more neutrino density is there. So neutrino over density is there for positive peak, and for the negative peak, we can say that there is no neutrino density or some other particle which are present in the plasma. So they will be present in those negative peak area. So from this plot, we have seen that our neutrino current first peak is around 0.02 GeV, and it is of alpha value is 2.3. So this basically this plot present the neutrino antineutrino density in the plasma. So this is the fluctuation of density. Okay. Now we will talk about neutrino density perturbation and electron density perturbation. Why we are taking we are talking about electron? Because see, we have taken our neutrino as our particle. So definitely neutrino will interact with our plasma. So we basically there will be two. It will be kind of two fluid description. So neutrino and electron, those two particles with coupled, their motion will be coupled with each other, and we will get some coupled equation for neutrino and electron. So as you can see, this first two equation has written for neutrino, and second two equation is for written for electron plasma. But in the second equation there is some contribution from electron plasma, and in the fourth equation there is some contribution from neutrino plasma. So basically these four equations are coupled equation. So hello.
Yes.
Oh, anyone is asking something?
No, go ahead.
Okay, thanks. So okay, from these four equations we can analyze the relation between neutrino and electron density fluctuation. So we are using some perturbative approach to open the relation, and this is our relation between neutrino density and electron density fluctuation. So see, in the previous plot, from that plot we are seeing that there is oscillatory nature in the neutrino density. So there will be fluctuation also, because there is a density in some place there is higher density, inside some place there is lower density. So there will be definitely there will be some number density fluctuation in the plasma. So we can relate here. So there definitely there will be electron density fluctuation. So if there is electron density fluctuation in the plasma, so what we can say that, so this neutral current means this neutrino current is indirectly generating a charge separation in the plasma. Like in some place there will be electron higher density, so that we can take as negative point, and in other place there will be deficiency of electrons, so that we can say as positive point. So basically we are creating two poles, one positive and negative poles, by the helping of this neutral current. So now we have two poles, so now we can generate a potential, and that potential can lead to field also. Okay, so now I will talk about the magnetic field part. So generation of magnetic field in the wake, as you can see that we are seeing this equation, that is BR1 battery equation. So first three terms are dependent on magnetic field, but this last term there is no contribution from magnetic field. So what we can say, if there is no initial magnetic field, as we are assuming for our case that initially there is no magnetic field, we are trying to create a small magnetic field. So if there is no magnetic field, then also this fourth term is the dominating part. So if there is number density fluctuation in the plasma and temperature gradient in the plasma, then we can generate a magnetic field in the plasma. And from the previous slide, from this slide, we have concluded that there will be a electron number density fluctuation, and neutron number density fluctuation is already there. So we will be using that electron number density fluctuation for our this Beerman battery equation. So we can eliminate this 3 term now. We can completely concentrate on this 4th term. That will be our magnetic field genetic term. So this 4th term is called the Beerman battery term. So here we have drawn a schematic diagram for the direction of this temperature gradient or density gradient. So basically Beerman battery equation works. So in the Beerman battery equation there is an number density fluctuation and temperature gradient, there is cross product. So we need to have a perpendicular relation between this density gradient and temperature gradient. Otherwise, that term will vanish. But for our case, we are having a 90-degree angle between temperature gradient and density gradient. So definitely, this model will, this Beerman battery equation will work for us. So from the diagram, if the density perturbation of neutrino is along y-axis, temperature gradient will be along x-axis. So using that xy direction, we have again written this Beerman battery term. Okay. So now we will try to estimate the magnetic field order. So temperature gradient across the cosmic string is of the order of 10 to the minus 5. So 10 to the minus 5 T. So we are calculating around like ElectroWeak scale. So it will be in GeV order. So here we have calculated in the order of in the temperature of 200 GeV. So this temperature gradient will be 10 to the minus 5 into 200 GeV. And GF is the Fermi coupling constant. So yeah, that is in the order of 10 to the minus 5 GeV minus 2. And from the plot, we have found for our plot that 0.02 GeV cube is the number density fluctuation. So now to evaluate the Beerman battery term, we have all the parameters. Like even all the parameters we are trying to evaluate the order only now, not the exact value. So to evaluate the order, we have all the parameters. So now after calculating the order, so we are getting approx order of 10 to the 13 Gauss. So yeah, we are getting a 10 to the 13 Gauss magnetic field. So now we are through this model, we are generating a magnetic field, primordial magnetic field. So but the thing is that we have some observed value from some radiation data, some other data. So according to the data, so at that temperature, the magnetic field should be in the near about like 10 to the 24 Gauss. It should be like that. So it is little bit small than 10 to the 24 Gauss. What we are getting, but the thing is that we can magnify this magnetic field. I mean, our magnetic field, we can magnify that magnetic field and we can reach this 10 to 24 Gauss value. So how we can magnify this value? So see, either that time plasma there is turbulence was there, and the plasma has higher Reynolds number. So this turbulence and higher Reynolds number will come to work to magnify the magnetic field. And beside this thing, so in this Beerman battery equation, previously we have taken B as 0. So we have evaluated the 4th term only. But now we have a small magnetic field for our case. So we can now if we put this magnetic field in this Beerman battery term, all these 4 term will contribute for our magnetic field. So through this Beerman battery equation also, we can magnify our magnetic field. So we can gradually reach this 10 to the 24 value. Okay. Now coming to the conclusion. So as we have proposed that neutrino density flux generates a charge separation in the plasma, and this charge separation form electron current in the neutral plasma. So indirectly, neutrino current, or more specifically, what we can say that a neutral current can generate a magnetic field. That is, so this is the main point of this whole work, that magnetic field which can generate due to only the charged particles. But we are here proposing a model where a neutral particle can contribute to form a magnetic field, and we successfully have get this order of 10 to 13 Gauss value. So yeah, we will later on we will do a detailed simulation of this magnetic field thing that will help us to understand that how much we can magnify this our 10 to the 13 Gauss magnetic field. So that will see later on. But for the time being, we have successfully proposed one idea that can generate a magnetic field in our plasma. So this work has published last year. So this is the title of the paper. So you can go and check the detailed calculation of the paper and all the other properties thing. So this is the cosmology group where I am working. So Dr. Soma Sanal is my supervisor, and other Abhishek and Somen is my collaborator. So they are throughout the work they are completely helpful. So I also want to acknowledge them. So okay, thank you. Thanks for listening to me.
Thank you very much. We have some questions.
Okay.
So let me ask a question. So, so you're saying that the neutrinos will be focused in the wake of the string, and that's what you're taking into account?
Okay.
Is that the mechanism? Yeah. So, but and this, how much they are focused there? Does it depend on the neutrino mass? How does it work?
What? Can you repeat the last line once?
So does the amount of the neutrino density which is focused there, does it depend on the neutrino mass?
Oh, you are asking that if this mass is dependent on this density or not?
Yeah. So
actually,
what is? Yeah. Go ahead.
Actually, what I can tell you that this cosmic string has a specific mass. So here, see this. Yeah, in this equation, see we were seeing this mu, that is mass per unit length for cosmic string. So how much particle with so how much massive particle can gather around this cosmic, that will be dependent on this like conical structure of the cosmic string also. So actually this cosmic string mass will contribute in that part. So like you are asking about that how much how much massive particle can gather in that place. So this cosmic string mass can contribute in that place. So if this is heavier cosmic strings, then there will be more massive particle will be attracted to near about region of the cosmic string.
Yeah, so I guess what I'm asking is, do particles with different masses concentrate more? So if I had a much more massive particle than neutrino, will it concentrate more there?
So actually, so you, I think you were asking that why I have taken neutrino as
exactly, yeah. Why the neutrino?
Okay.
Yeah.
Thanks. Okay, so the thing is that what we while starting our work, what we have thought that so we are doing in ElectroWeak scale. So the better choice maybe this electron. Okay, so because electron will be more massive than neutrino. But the problem is that what we have thought that if in the plasma, so in that time the plasma was neutral. So if we are trying to generate this charge separation, actually the what charge separation we have generated, that is locally we have generated this charge separation. So globally the plasma is neutrals. So for the electron case, so there will be at some place if there is one electron, so due to the property of charge neutrality, by default there will be another positron will also be present there. So if we are trying to analyze the motion of this electron, and we are trying to trying to understand the contribution from the electron to this magnetic field, so there will be one equally opposite contribution from this positron. So that will neutralize the effect of this electron thing. So that's why we don't want to actually we don't want to take electron for our particle. And another thing is that so to generate this motion, there should be some asymmetry. So they at the temperature neutrino asymmetry will neutron antineutron asymmetry will be there. So there will say this handedness asymmetry is there already. So that's why this neutrino. So if a neutrino contribution will be remain in the plasma, and I have mentioned in one slide that whatever calculation we have done for neutrino, we can do the same calculation for antineutrino also. Only one parameter will change. See, this beta will change the sign. For neutrino it will be plus and antineutrino it will be minus. So when we are trying to calculate the current, that time we are doing side against side. So anyway, this minus will cancel out. So while when we will try to calculate the current, so for neutrino and antineutrino, for both the particle, we will have a positive contribution to the magnetic field, and they will not neutralize their effect.
Okay, all right, thanks.
That's why you have taken neutrino.
Other questions? Okay, so it looks like our second speaker for the day did not join us, so the whole schedule will be shifted up. Would that be okay with the other speakers? So Masud, would that be okay if you start talking at 15 past? And then followed by Mercedes.
And
Neki. Sorry?
Yes, I am ready for a quarter past.
Quarter past 5, yes.
5. Yes, I will.
Yes. Okay.
Yes, it's fine.
Thank you. And Mercedes, that would be fine to shift?
Fine with me. Yes, fine with me as well.
Yes, okay. And Key?
No problem.
No problem. Okay, very good. So we have a break for actually 35 minutes as it seems. You can, yeah. So it would be good if we are all back here maybe 5 minutes before, so that we don't start late. And I think the session stays open for the time being, but if people want to discuss, please, you can go to Mattermost. That would be the easiest. You can also, just to remind you, you can create your own private chat rooms for discussion. Okay, thanks for the first 3 speakers, and see you soon in half an hour.
Okay, thank you, Costas.
Thank you. Hello, Masud.
Disposal.
Okay, so would you like to load your slides?
Yes.
Okay, let's wait for a minute.
Hello? Yes.
Yes. Let's wait for one more minute and then we'll let you start.
Yes. Good evening and good morning, whatsoever it is.
Actually, I think so. It's already 15 past, so we can already start. So welcome everyone back to the Astro-particle physics and cosmology session. And our next speaker is Masud Chaichian. So Masud, you can already start your presentation. Thank you.
Thank you. So good evening and good morning or whatever it is. I would like here to talk about the possibility that one can avoid the assumption of Lorentz-invariance violation in order to explain the gamma ray burst delay. These gamma rays travel through the interstellar space, and they have been experiments that people have used it for Lorentz-invariant violation. This work has been done together with Iver Breivik from Norway and Kotaescu from Romania. So experiments in Antares experiments taken through the years 2007 to 2012, and these are all the references, and at the end there will be a full reference. And they observed that the burst of gamma rays, which travel through stellar space, they have delay of a few hours or up to 1 day or so, compared with the neutrino burst. So the assumption has been by the experimentalists, astronomers, that this gamma ray burst and neutrino burst have emerged from the same source and at the same time. Now, there has been a big activity, both theoretical and experimental, to assume that this delay of gamma ray has been due to Lorentz invariance violation. But is it really necessary? Because when we break special relativity, which is in this case, but we don't break general relativity, which is based on it. I will come to this point later. Now, maybe we can start to explain this gamma ray burst delay by standard physics, and namely by dispersion of light traveling through the interstellar space. So we know that when light comes through a medium, it disperses. We know from usual experiments, life-day experiments and experience. And so we have to take for this medium, interstellar space medium, some medium. For example, let's start with the electron plasma. Why plasma? Because the wavelengths of this gamma ray bursts are much smaller than the distance of the this gas. So in this case, this is called simply plasma. So in this plasma, from usual classical electrodynamics, these are the book stuff, like in Jackson's book or my book and with collaborators, that the frequency of the light has the usual one, this term, plus it is called plasma frequency. It means when the photon hits the electron, in this case, electron plasma, then plasma oscillates and it has a frequency of as like this omega plasma. Now, omega plasma, from classical electrodynamics, we know that this is this formula, that it is proportional to electron squared. This is the coupling constant, and the number of electrons, density of the electrons in this medium, and divided by mass of electron. So, but the same formula as above, this one in classical electrodynamics, can be also obtained in the limit of the from quantum field theory, or namely green functions methods, which, for example, is very well presented by in the book, classical book of Abrikosov et al. And in this case, it is just the green function, like amplitude of photon hitting electron, giving electron, and then another photon and electron. So there is a vertex here, E, electron vertex coupling, and this is another one. And then the propagator of the electron here, it is Dirac propagator. But as the Q, the transverse momentum between electron and photon is very small, we can forget this term. So we get this formula for the plasma as here, square of plasma frequency for the electron. Now, if we take the mass of electron and we look at the group velocity which photon or gamma ray burst obtains when it is in the medium. It is the usual C minus something. It means the dispersion of the light, as usual, is less than speed of light. Now, for example, if we take the gamma rays energy of 1 TeV, in this gamma ray burst is something between 1 TeV up to 100 TeV, very, very high energies. So we put 1 TeV and we find that the velocity of this light, group velocity, is C minus 1 multiplied by N. N is the density of the electrons in the medium, in the plasma, 10 to the power minus 51. Unless we put very huge N, this number will be the same, the velocity of the light will be the same as the speed of light in the vacuum. So dispersive properties of electron in a plasma of electrons is not significant to account for a delay of a few hours, let's say. Now, which other possibilities we can find which maybe will help to explain this delay of the gamma ray burst? So, of course, there is a cosmic background, which is, of course, very little contributes to electron, the light scattering, because it's the fourth order in quantum electrodynamics, right? So that there is no good if we have cosmic microwave backgrounds we include. That is very small. so what about axions, which has a mass of the order 10 to power minus 5 electron volt? This is assuming that axions are some hypothetical but real particles. I mean, they exist. For that, there was a talk of Franco where he explained that how many problems are solved by the existence of axions. We solve dark energy, dark matter, and CP, strong CP violation. And here also it would help. But we cannot use this formula because here enters the coupling of the axion to photons. But all the axion models, they are not charged, they are charged, they are neutral. And in activity of an axion in electrodynamics has been tremendous, starting by, of course, we know Quinn and Paniccia, and then Wilczek, and all these people have written, have done a lot of contribution. And this experiment at CERN for the Axion Solar Telescope and many others Fernando mentioned. And also, in addition to those properties, it has connection to topological insulators in solid state physics. So, assumption of an axionic plasma with this coupling to photons seems not natural. It seems natural, actually, to take such a. Now, photon axion coupled also to electromagnetic field through the kind of loops, and it couples to two photons by interaction Lagrangian, which is given by several people. For example, in this paper, it is the normal through the QCD calculation, and this one is in string theory calculation. And the Lagrangian is famous. This also wrote Fernando, and the coupling comes as of the coupling of the axion to two photons is according to this formula, all these coefficients here, and these values are given, estimated by those people. And the coupling of the axion to two photons is of the order of 10 to power minus 12 let's say the lower limit is 10 to power minus 10 GeV to power minus 1. Of course, it's very small. That's why it's dark matter. Yeah. Now, in this case, what is the dispersion of light in axionic plasma? It is the same as formula as before for electron. However, the plasma, which is axion, will be the density of axions multiplied by this coupling of axion to two photons. This is the plasma frequency. Now, N is the mean number density of axions in the cosmic plasma. Now, with the value of coupling constant of axion to two photons of this order, and assuming that N axion is, it means it is the number of the axions in cubic meter, is very huge, 10 to power 51, 10 to power, or let's say the less 10 to power 49. We can calculate by that formula. It was written how much time delay will be of gamma ray burst compared to neutrinos. So this delay will be about several hours, which is a good number within the experimental delay. Now this, for D, what we have taken here, we have taken the D like as an estimate. They travel, distance traveled by photons, and we take it for an estimate to be the diameter of observable universe, which is at the moment is 10 to the power 26 meters. But of course, the number of the density of axions in interstellar space is a function of place in the medium it passes. So it is distance dependent. This we have not taken into account because these are the details. For estimate, it is sufficient to have that space. While nearby to us, very high density of axions is not natural, but at very far distances, near this stellar space, where there are existing many heavy galaxies, an axion will be by far larger, because the same way as axion couples to photons, axion also couples to two gravitons. So the coupling increases, and the density of the axion near the huge, massive galaxies can be very much different and higher than now. In addition, what has been done this for the evaluation of the plasma frequency? We have taken only the electric part of the interaction, but we know that because we have assumed this as a normal medium, but for electron plasma, we have not taken any magnetic contribution because these are all in the classical electronics because of parity of the medium. If it is usual medium like electron, parity is conserved. But for a chiral medium, as is called by Wilczek and the others, where there is the parity violation because of existence of axions, then the magnetic also contributes. So therefore, the omega plasma can be also bigger if we calculate it more accurately. And by the way, such a chiral medium with magnetic contribution affects the Casimir effect. And you have some two solid state physics where they are axions. So this is another indication that N is not natural. The density of axions we have taken is natural. Now, a large activity in general for gamma ray bursts has been started by this seminal work of Jacob at Piran. These are astrophysicists, and in those years, and what in the Lorentz-invariance violation now method, how is the Lorentz-invariance violation for explanation for gamma ray delay? Special relativity dispersion, which is for photon without mass, is this part. Now they add another one, which makes the effect of reducing this formula will reduce in high energy to such a velocity for the photon in the because of Lorentz-invariance violation less than c, the usual speed of light. And this is the energy of medium, this is the energy of light, and this is assume that this is a quantum gravity effect which does not exist, but this is assumed that in quantum gravity at very high energy, the Lorentz invariance is violated. And then this quantum gravity is taken to be 10 to the power 16, and psi and the data are also fixed. Now, now let's compare these two formulas. If we take a cosmic plasma, it means dispersion of light for this delay, or we take the Lorentz-invariant violation. You see, this is the formula. And then we can see that energy dependent of the delay. It means if the cosmic rays are higher because the energy will be here down. So the delay becomes less. And in the other case, the more energy of the ray, the delay becomes more. So energy dependent of day and cosmic plasma. In cosmic plasma case, higher energy gamma rays gives less delay, higher energy gamma rays, more delay. And further future experiments will resolve this. These future experiments will resolve this solution. Now, for neutrino, if we take also its oscillation, also, and we know that neutrino with the medium has very negligible interaction. It means dispersion one can neglect. And then from this formula, relativistic formula, usual Lorentz invariant special relativity formula, the velocity of this neutrino will be, because of it has a mass, will be 1 minus this. And when we evaluate this for 1 TeV, we will get 10 to the power minus 26. It means the assumption we have made that neutrino comes with no delay has been all right. It is like C. So big questions arrive in the case of Lorentz invariant violation, because unless one changes the dispersion relation for neutrino and photon, there will be no difference. They will come at the same time. You see, because you should have a universal formula for the dispersion relation and not dependent on the process. Now, this delay of the photon rays at the same time can shed the light on the Abraham-Minkowski controversy. Abraham-Minkowski controversy is as old as more than 100 years. Abraham momentum connection and the Minkowski momentum correction is by this formula. It means this is the Abraham and this is Minkowski. Now from here, in this case, when we take H omega P over Hk, this is the energy for the light and this is momentum. Minkowski momentum will give less velocity for the photon, and in this case also momentum, Minkowski momentum is favored the same as the laboratory experiments, because theoretical one cannot resolve this controversy. There have been hundreds of papers, but only experiment and laboratory experiments in solid state physics have been showing that. Now, the conclusion is very simple. While we do not underestimate the interpretation of gamma ray burst delay by assuming Lorentz invariant violation, we bring attention to another possibility of its explanation by standard physics of dispersion of light through a cosmic plasma, assuming to be axion plasma. So if axion exists, this can be explained as well without Lorentz invariant. So what is good is that future planned experiments will resolve between the two possibilities. That is, if they can delay of the light, whether it is energy dependent and in which direction, because the prediction are quite opposite. Thank you.
Thank you. Are there any questions? So just one brief question. So you mentioned that the effect depends on the number density of axions.
Yes, yes, very
yes, but not on the mass density of axions. So is there some upper bound on the mass of the axion that you can allow?
No, it's not. It is not depending on the mass, only on the coupling of axion to two photons, which has been calculated by many authors, and also in QCD, and also in string theory, coupling constant, and the density of the axions in the interstellar space, right? Only this one parameter is this, the number density.
Okay. If I assume that the density of axions is not much bigger than the average density in the universe, can I convert that? Or that's not it?
Yeah, you see, they are upper bounds of density of axions, but they differ from each other by order of magnitudes.
Okay.
But near the stellar objects, which are heavy galaxies, because the gravitational field is very strong, they can be much older than average. So this will affect, you see. So there is not anything against in that, at least theoretically, until now.
Okay, and how does this controversy enter, though, the axion calculation? Is it unrelated to it? So you mentioned there is this controversy between which momentum is the right one that affects the calculation involving the axion, so that's something independent.
You mean for the density, right?
No, for the controversy between which momentum is the right momentum to use.
Yeah, actually, the only different evaluation comes for the coupling constant, and the energy dependence is always the same. The more energetical photons, I mean gamma ray burst spectrum, the delay is less, and the least energy of the gamma ray burst, the delay is more. And in the Lorentz-invariant violation interpretation is just the opposite. So it is very easy to resolve this difference, to see which one is really correct.
So I have a question by Adam Smetana. Please unmute.
Hello, can you hear me?
Yes.
Hello?
Yes, I can hear.
Thank you very much for this nice talk. I am interested how is these formulas for the change of group velocity, how is it derived? Can you please maybe tell me what are the relevant references where I can find
you know, the group velocity in the classical electrodynamics, which is also the group velocity in the relativistic case, special relativity. This is the formula, the derivative of energy.
Yes, sure, but I mean, sorry, I mean the formulas which are actually expressing the group velocity changes in the medium of axion and or in other medium. You know, you were showing this.
Yes, of course, in the medium of axions and in space, and also in the for neutrino and for gamma ray bursts are all different because they are different.
Sure. And one can calculate it. I guess one can calculate it from the knowledge of the cross section of gammas with the medium particles, right?
That is also true. Yes, of course.
And can you tell me what is some, or what would be the reference to look at it in more detail, or maybe in your papers? Is it calculated?
No, in these papers have not been yet submitted because this is just being finished.
So
then, but the velocity in the relativistic theory, I mean, in the special relativity, it is always the derivative of E over dp. That's why this controversy between the Abraham and Minkowski arises, you see, because here this is Abraham, and then if you take the derivative, the velocity will be more than c, group velocity, and here the opposite. You see, when we take derivative of it, E will be this. It means the velocity will be less than the usual velocity. This is called the group velocity, contrary to the particle velocity. Like because there is a wave-particle duality, right? So there is light can be considered as a particle with photons, or like wave lights, right? So this is the formula for the group velocity.
Okay.
And these are all in the classical electrodynamics and relativistic electrodynamics. In those books, I mentioned this, for example, no? Because these are very detailed, or in our book, also very detailed, are given the formulas for velocity and also for the.
Okay. I will check the book. I will check the books. Thank you very much.
Yes. Thank you.
Thank you.
Okay. There are no more questions, so let's thank our speaker again and move on to the next speaker, who is Mercedes.
Yeah, I cannot start the sharing if the previous speaker doesn't.
Yes.
Yeah, thank
okay.
you.
Yeah, thank you. Okay, so our next speaker is Mercedes Paniccia, who will discuss new results from AMS.
Yes, thank you. I will present the latest results of AMS on primary and secondary cosmic rays. There's something. Yeah, so primary cosmic rays are elements that are created in the stellar nucleosynthesis inside stars, like like protons, helium, carbon, oxygen nuclei, and also other heavier nuclei. And these are produced along the lifetime of the stars. And when at the death of the stars, when it explodes in a supernova, they are accelerated and ejected in the interstellar medium. Other nuclei, like lithium, beryllium, and boron, which are not abundant products of stellar nucleosynthesis, are instead created by spallation of primary cosmic rays with the interstellar medium. That is a collision of primary cosmic rays while they propagate through the interstellar medium. And so these are basically lithium, beryllium, and boron for what concern the nuclei of charges less than 10. Let me briefly introduce the alpha magnetic spectrometer. It is a TV precision magnetic spectrometer where we have several detectors that redundantly measures the charge and energy of particles. So let's start in the center of the detector. We have 7 layers of silicon tracker inserted in a permanent magnet. This allows to measure the rigidity, that is the momentum divided the charge of the particle by the bending of the track, so to identify also the sign of the charge of the particle. By the deposited energy, the E and the X inside the detector material, we can also determine the absolute value of the charge. Below and above the magnet, there are two double layers of scintillators that compose the time of flight, which provides the main trigger to the detector, and also provide a redundant measurement of the charge of the particles, and it measures the beta. On top of the upper top, we have a transition radiation detector whose main purpose is to identify light particles like leptons, electrons, and positrons against protons. So one has to take in mind that protons are the most abundant species in cosmic rays. Then at the very top of the detector, we have an additional silicon tracker layer. Below the magnet, we have a rich ring imaging Cherenkov detector. And below that, a last silicon tracker layer 9. Finally, at the bottom of the apparatus, there is an electromagnetic calorimeter which provides 4% accuracy measurements of the energy of electrons and positrons. So we have redundant measurement of both charge and energy by several subdetectors. For the rigidity determination, as I said, is determined by the silicon tracker layers for the magnet. We have in total 9 layers. The lever arm is from tracker layer 1 up to tracker layer 9 is of 3 meters. This translates to a spatial resolution of 10 micrometers for protons, 5 to 7 micrometers for light nuclei, so from helium up to oxygen, and 6 to 8 micrometers for heavier nuclei from fluorine up to silicon. The spatial resolution is directly translated into the maximum detector rigidity, which is of 2 TeV for protons and ranges from 3.2 to 3.7 TeV for nuclei from helium to oxygen, and of 3 to 3.5 TeV for fluorine up to silicon. So for the determination of the accurate determination of the flux, is it crucial to know the absolute rigidity scale of the detector. It has been calibrated at test beam before the flight, but at the launch to the International Space Station, and also during the flight, because of activity on the International Space Station, visiting vehicles or rotation of the solar arrays, smaller movements can happen that can shift the rigidity scale. So we align the two external layers, layer 1 and layer 2, in flight using cosmic ray protons every 2 minutes. And they are stable to 2 to 3 micrometers, as shown by the picture below, which show the residual in the measurement of the coordinate as function of the time. The in-flight rigidity scale shift and its uncertainty are obtained comparing the inverse of the rigidity measured by the tracker for electrons and positrons with the energy measured by ECAL, the inverse of the energy, as shown in the bottom right plot. This is done in 72 rigidity beams, and this allows us to determine the rigidity scale shift with an accuracy of 3% at 1 TeV. And for nuclei identification, the main detector that we use is the TOF and the tracker. And here you can see the identification of nuclei from protons up to cobalt and nickel by the TOF and the tracker. The insert on the upper right shows the tracker charge, the relative charge resolution. So we have published so far in physical review letters the individual fluxes of nuclei from proton up to oxygen, and very recently for the group for neon, magnesium, and silicon. We are now finalizing the measurement for heavier nuclei like sulfur and iron, which are also primary, and for fluorine, sodium, and aluminum. In as of today, in 8.5 years operations. We have collected more than 160 billion cosmic rays. Recently, we have updated all our results with a 7 years data set. And these results have been collected to a paper submitted to Physics Report. So I will present these new results based on the 7 years data set for protons up to oxygen. And Jian will present after me for the group of neon, magnesium, and silicon. So let's see the proton spectrum, which is the flux multiplied by the rigidity to the 2.7. The red dots are the new measurement by MS with a 7 years data set, which is an update of our previous publication in PRL. This data set contains 1 billion proton events. As you can see, the spectrum cannot be fit by a single power law, which is the dashed blue line, but is well fit by a broken power law, where we have a characteristic transition rigidity R0, a spectral index before the characteristic rigidity R0, and a delta gamma, which is the amount of the spectral break, and S is a smooth transition. So what we found is that the characteristic transition rigidity is at around 331 gigavolt. The spectral index is minus 2.85 before 300 gigavolt, and the break is the delta gamma. The hardening is of 0.22. Let's now look in more details the behavior of the flux, looking at the spectral index as function of the rigidity. This is measured by derivating the derivative of the log of the flux with respect to the log of the rigidity. And it is done in independent rigidity bins. We find that the proton spectral index increases progressively above 200 GeV, so the spectrum has a break at about 200 GeV. Now, to measure nuclei, it's important to know the interaction cross-section in the MSA material, which is done mostly of carbon and aluminum. But inelastic cross-section data available are only restricted to few target and projectile nuclei. And moreover, there are no measurements available beyond 10 GeV. But we can measure the survival probabilities of nuclei with MS in flight data. We used the so-called horizontal runs, where the ISS was running in an horizontal attitude. In this case, particles can enter from the tracker layer 9, so from the right to the left, as depicted in the bottom drawing. So we use the tracker layer 2 to layer 8 layers to identify the incoming particles. The target is the material in the TRD and the TOF, and then the outcoming particles are identified by the tracker layer 1. Similarly, we can measure the survival probability in the lower part of the detector, which is the lower TOF and the tracker layer 9. Again, these are particles entering from the left to right in this drawing, with the beam identified again in tracker layer 2 to layer 8. We can measure the survival probability from layer 8 to layer 9, and not only during these horizontal runs, but also in a normal operation condition, because normally the particle enters from the above, so from tracker layer 1 down to layer 9. So then we have produced a dedicated Monte Carlo sample where the giant 4 Glauber-Gribov model in elastic cross-section have been varied by plus minus 10% to choose the one that best agrees with our measurement. In this picture, I show as an example the inelastic cross-section of helium to carbon target as measured by MS in red lines, plus the band shows the uncertainty, compared to the dashed blue lines, which shows the giant 4 original Glauber-Gribov model, and available previous measurement on target at test beams. So Jian will talk more about the determination of nuclear cross-section for heavier nuclei, and now we can model these cross-sections. So this is our updated measurement of the helium spectrum based on the 7-year data set, which contains 125 million helium nuclei. As seen, also helium shows a spectral hardening at high rigidity. The transition energy rigidity is also around 350, as we have found for protons. The spectral index before 300 gigavolt is a minus 2.75, and the hardening is of 0.16. Again, a better understanding of the spectral behavior is given by the spectral index as function of rigidity. This is our measurement, and again we saw a hardening at our above 200 GeV. If we compare with protons, we found that the spectral indices are different, but at high rigidity they tend to a common value. We can investigate this further by looking at the proton to helium ratio, shown here by the red dots. And we see that it can be well fitted by a constant term A plus a simple power law with spectral index 10 delta equal to minus 0.3. And notice that the power term, the power law term contribution seems to vanish at high rigidity, so the proton to helium ratio tends to a constant value. Let's now compare helium, which is one of the primary cosmic rays, with carbon and oxygen. In a 7 years data set, we have 14 million carbon events and 12 million oxygen events. And these are the spectra of helium, carbon, and oxygen put together. You see that the shape is at high rigidity is similar. Again, looking at the spectral indices as function of rigidity for the 3 nuclei, we found that they all harden above 200 GeV, and in an identical way, the spectral indices are identical above 60 GeV. Now, to understand the origin of this hardening, we can investigate how are the spectra of secondary cosmic rays. In particular, lithium, beryllium, and boron that are produced mostly from collision of primary cosmic rays, carbon and oxygen, with interstellar medium. So cosmic rays are commonly modeled as a relativistic gas, which diffuse into a magnetized plasma. Diffusion models based on different assumptions predict a secondary to primary ratio that is asymptotical proportion to a rigidity to the delta, so to a power law. The delta assumes different value depending on the turbulence model that is realized. So if the Kolmogorov turbulence model is realized, then delta is minus 1/3, while the Kreisner theory predicts a delta of minus 1/2. So if the hardening we observed in primary cosmic rays is related to the...
Mercedes, may I ask you to accelerate a little bit?
Yes.
We don't run out of time. Yes.
Yes. To the injected, so if the spectra is already, the spectral break is already at the source, then we expect the similar hardening in the primary and secondaries. While if it is due to a propagation properties, then we expect the hardening stronger for secondary. So secondary should be twice the effect we see in primaries. And here I show our measurement of lithium and boron. So let's see first, the spectral shapes for lithium and boron are identical above 7 GeV. If we compare beryllium to boron, what we find is that the 3 primaries, lithium, beryllium, and boron, have identical rigidity dependence above 30 GeV. The difference that we see in the shape and low rigidity is due to the presence of the radioactive isotope beryllium-10. So the isotopic composition of lithium and beryllium will be presented next Thursday in the parallel session by Joey Wei. So let's now compare the spectral shape of the primary with the secondary, and we see that primaries group together, the 3 secondaries groups together. So primary and secondary have distinctly different shapes. This is also seen in the spectral index. We see that both deviates from a single power law above 200 GeV, but secondary are then more than primaries. This can be better investigated by looking at flux ratios. So here you see the flux ratio of boron, beryllium, and lithium to carbon, and flux ratios to oxygen. So this can be we have been fit with the power law in rigidity intervals from 60 to 192 GeV and from 192 to 3.3 TeV. What we have found is all the ratios exhibit hardening, and the secondaries are then more than primaries. If we put together these fit results, we see the spectral index in the two rigidity interval. So combining the 6 secondary to primary flux ratio, we find an average hardening at 192 GeV of 0.140 plus minus 0.025. So the significance of this hardening is found to exceed 5 sigma and supports the interpretation of the flux hardening as a universal propagation effect. So last, I will show you the flux of the nitrogen, which is partly primary and partly secondary. And so our measurement here are the red dots, and it can be well fitted by a secondary component and plus a primary component. We took a secondary component proxy, the boron shape, flux shape, and for the primary, the oxygen. And by this fit, we found that the ratio of nitrogen to oxygen at source is at 0.09 plus minus 0.02. On the right, you see the spectral index of nitrogen compared to the group of the 3 primaries, helium, carbon, oxygen, and the 3 secondary, lithium, beryllium, and boron. So the nitrogen spectral index is situated between the primary and the secondaries. It hardens rapidly with rigidity above 100 GeV and then becomes identical to the spectral indices of primaries at 700 GeV. And this brings to my conclusion. So I have presented the fluxes of protons, helium, carbon, and oxygen, and secondary lithium, beryllium, and boron obtained with the 7 years data set of AMS from the GeV up to few TeV. All primary spectra deviate from a single power law above 200 GeV. The proton to helium flux ratio is well described by the constant term plus a single power law term that vanishes at high rigidity. And the helium, carbon, and oxygen have identical spectral shape above 60 GeV. Secondary nuclei, lithium, beryllium, and boron, deviate from a single power law also at 200 GeV in an identical way, but exhibit an hardening larger than those observed for primaries. The average hardening is of 5 sigma level, and this observation favors the hypothesis that the flux hardening is due to an universal propagation effect. Then I presented the nitrogen spectrum, which is well described by the sum of primary and secondary component. We will measure in the future, we are working on measuring the heavier secondary nuclei fluxes. And these are my conclusions.
Thank you very much. Let's move on to questions. So let me start one quick question. So from the theory point of view, what would be this? So you mentioned this flux hardening as a universal propagation effect. What would be the theoretical explanation for that?
Okay, there are several models that have been proposed. There can be a break in the diffusion coefficient, or that probably the distribution of matter is not uniform in the interstellar medium, but there is still no clear how to say. Other authors propose that there are 2 different acceleration mechanisms that intervene at different energies. but the disentangle between these two models is not still, they're still debated. Both are viable.
Questions? Let me see some hands. Okay, so thank you very much. And let's move to our next speaker who will continue on AMS. Our next speaker is Jian.
So okay, I will start my talk. So I'm Tian from MIT. So I would present the property of the neon magnesium and the silicon primary cosmology result from AMS. So as introduced by the previous speaker, that AMS did a measurement of cosmic spectrum. And for this talk, that I will talk more about the so-called primary as cosmic for the high charge. So one of the fundamental measurement in cosmic ray is the determination of the energy relation of primary cosmic ray, like the proton, helium, carbon, oxygen, neon, magnesium, silicon, out to iron. These are thought to be produced and accelerated in super realm in our galaxy. This station carries the information about the cosmic ray accelerations in astrophysical sources and the propagation in the galaxy. So that here the typical just to see that the primary cosmic ray are injected from a supernova, and then it propagate through the interstellar medium and eventually detected by our detector. And those kind of like primary cosmic ray can also interact to be like the lithium beryllium boron, so-called the second cosmic ray, and also detected by our detector. So AMS performs the measurement of the cosmic ray light nuclear from the helium to oxygen, and we measure the spectrum up to the 3 TeV energy range. So as described by previous speaker, we first published result on helium, carbon, oxygen, so-called primary group, and we observed the 3 elements have a very similar rigidity dependence above 60 GeV. And all of them are derived from single power law and hardening in identical way. And the second paper, we published the result on the secondary cosmic lithium beryllium boron. And the interesting is that we observed that all the 3 also have identical rigidity dependence above 30 GeV. And we also observed in the secondary cosmic that has also the so-called hardening of the spectrums change derived from a single power law. And the more important, we observe this kind of the hardening in the secondary is about twice than the primary. So this is a very important observation. And in the latest paper, not the latest, but I would say the last paper in the 3, we also measure the nitrogen. So the interesting nitrogen is can be well described by a linear combination primary and the secondary over the entire rigidity range. So here it shows the 3 reference and the details introduced by the previous speaker. So in this talk, I will cover the so-called measurement of the primary cosmic rays, neon, magnesium, and silicon. And here shows that for all the charge elements displayed in our detector, one is measured by our time of flight detector, another is measured by our charge detector. So by owing to our very good resolution, we can identify all the elements from the proton up to the nickels charge equal to 28 and all the elements. And I would more talk about the neon correspond charge equal to 10, magnesium charge equal to 12, and the silicon charge equal to 14 elements measurement. So there'll be some measurement of the primary cosmic ray neon magnesium and silicon fluxes before AMS. So this plot shows that all available measurements of the three spectrums before AMS. So from this plot that here, due to the limited accuracy, we cannot well know the behavior of all the three element fluxes in cosmic ray. And AMS performs a measurement cosmic nuclear for these three elements 10, 12, and 14 charge is done based on the 9 layer of silicons plus magnets. So the silicon chocolate from the top is layer 1 and 2 to 8 in the inner part, and then the layer 9 is the lower part. So we use the kind of chocolate plus a magnet to measure the rigidity, and this is correspond to the momentum per unit charge. And for z equal to 1, we have a coordinate resolution around 10 micron for each individual layers. And as there are more larger energy deposition, this resolution would improve the functional charge. And for 9 to 14, we have a resolution 6 to 8 microns. And over the 3 meter level arm that we eventually can reach 3 TeV measurement rigidity. And velocity and direction can be accurately determined by our time flight detector. We have a resolution on the velocity is 1% of all three elements. And from the top, the real ones and upper 12 and inner chocolate 2 to 8 and lower 12 and the real 9, we can check the consistent charge along the particle trajectory. And for the 9 to 14, we have very good resolution. Take example of using the chocolate layer 2 to 8, we have a resolution 0.13 to 0.17 charge unit. So this would ensure that we have a clear, very good identification of the different elements for the three nuclei. And the example shows that we can look on the charge distribution, like the measured by all the layer 2 to 8, the 7 layers of the chocolate. And then we can display all the different elements. And the dashed lines indicate the oscillation of 3 elements for the neon, magnesium, and the silicons. So from here, that distribution, we can see that we can identify the 3 elements basically without any contamination. However, there's an issue how to treat it is that we also have a minor background. And the background resulting from the heavier charge that could interact between a chocolate layer 1 and the layer 2, so the inside of AMS material. For example, the magnesium and the sodium, it could interact with the neon. And this background can be subtracted by using the layer 1 charge measurement. So after this substitution, the background is very small, to be less than 2% in the interior energy range for the neon, magnesium, and silicon. So this plot illustrates when we're using the inner chocolate 2 to 8 to identify the neon, that only the external we have 1 layers on the top to identify charge elements. Then we look on this layer measurement, we can clearly see all components of the neons. Original neons, and we can also show that the composition from the sodium interacting to the neon and the magnesium interacting to the neon. And eventually, after we import the cut as shown in the dashed line, so basically we can reject all the higher elements in direction background. Another important to perform measurement is for the relate to the energy measurement. So AMS do this measurement rely on the chocolate coordinate need measurement. So the AMS chocolate together with the magnet to the rigidity, so-called the momentum per unit charge of the charged particle. And the observed bending coordinate resolution is like shows in the left panel, 6.7 microns derived for the neon, 7.1 microns for magnesium, and 7.4 microns for silicon. So these resolutions were understood in our detector, as shown in the red histogram that the Monte Carlo simulation is well produced for all the kind of response in our chocolate. Therefore, that eventually after detailed study, we can achieve very small systematic error on fluxes in the level of less than 1% below 300 GeV and reach 2.5% at the 3 TeV rigidity. So another important ingredient to perform the precision measurement of fluxes for the nuclear is related to the nuclear enlarged interaction. So AMS is also able to perform this accurate study on the nuclear interactions. So the AMS material is composed primarily of the carbon and the aluminum. And the survival probability of nuclear due to enlarged interactions with the detailed materials are important for determination of cosmic nuclear fluxes. And this can be well also accurately measured by AMS. And for instance, for high Z nucleus, a foreign method was used. So the first we can select the primary nucleus by using the top measurement, so-called layer 1, first layer of detector. And then we can obtain by comparing the charge measured with the inner chocolate 2 to 8, as illustrated in the left panel. So the first on top we select, for example, to be magnesium, and then we can look at the inner measurement charge elements. So this element could be still survived magnesium as shown in the red panel. And those magnesium could also interact to the lower charge like the sodiums, neons, and all other elements. And the black dots shows our data measured the distribution for the different interacting elements, and red histogram shows simulation results. So from here that we can see that all the different channels are well produced in our simulation. And AMS is able to perform this kind of nuclear interactions, breakup channels, look at every channels, for example, as a magnesium. So first, as I explained before, that we could select the first layer to be the magnesium and look on the inners, and then calculate the probability of magnesium to fragment to the different elements. So we can take example like the magnesium to the sodium channels, and the black dots, so the field dots show the AMS measured probabilities as a function of the rigidity. So our measure value is between around 5 to 6% for the data, and the open circuit also show the simulation, and it will produce our data result. And another example could be also seen on the forings, and the Monte Carlo data has well agreement. And the detailed introduction can be found in this reference, and I would not spend more time on that. And eventually we can even derive the so-called nuclear to carbon interaction cross sections. So AMS has performed the measurement element from the heliums, borons, carbons up to the irons, measure the nuclear to carbon interactions. And if you look on the square root of the interaction cross section at the rigidity 50 GeV as a function of the charge radius. So the charge radius is obtained from other experiments shown in this reference. And the cross section is measured from AMS. We can clearly see the linear correlation between the two measurements. So this probably can be well described by a simple optical approximation by the so-called square root cross section related to the two charge radius of the project and the target. And there's also inactive areas in the correlation. And this describe all data rather well, and give a K-square 2.89 divided by 8. So and then eventually that for the parameter, the K is shown in these values, and also quoted so-called uncorrelated error fit, and also the material errors. And here also show another parameters. So the detailed description of the method is also described in this paper. Then after the detailed study, we can achieve the systematic errors on the neon, magnesium, and silicon fluxes due to the uncertainty in the evolution of the nuclear interactions to be very small numbers to be 3.5% up to 100 GeV and less than 4% from 100 to 3 TeV. And this can be only achieved with accurate measurement from AMS. And after all the details discussion about the measurement, eventually I will share with you the AMS measured fluxes on the neon and the magnesium. And this corresponds to 7 years of AMS data taking. And this important result has been published in this latest papers on 2020s. And the measure interval is from the 3 GeV to the 3 TeV rigidity. And the triangle shows a neon flux amount by 1.2 and compare the flux measured from the magnesium. So from the plot, we can see that the two fluxes have very similar rigidity dependence at the high energies. And the detail can be looked when we perform the ratio of the neon to magnesium. And low energy we can able to describe by a single power law, and high energy will be constant. So it means above 3.865 GeV, the neon and the magnesium have identical rigidity dependence at high energy. And we can also compare the measurement from the magnesium and compare the fluxes with respect to the silicons. And the measure range from the 2 GeV to the 3 TeV, and the silicon fluxes is more by 1.1 and compared with magnesium. And below panel shows the ratio of the silicon to the magnesium. And the low energy can be described by a single power law, high energy is constant. So it means that above 86.5 GeV, the silicon and the magnesium have an identical rigidity dependence. So, and more detail can be looked on the neon, magnesium, and silicon spectrum index. So take an example, the spectrum index is calculated from the d log flux divided by d log r. And for neon, for example, the triangle at the low energy close to 10 GeV, its spectrum index is minus 2.3, and the gradually decrease to minus 2.8 at 100 GeV. And the high energy it start to raising, so-called hardening. We observed all in the 3 elements. And also we observed that for high energy, the 3 have a very similar spectrum index. And eventually that here MS observed the neon, magnesium, and the silicon spectrum index have identical rigidity dependence above 86.5 GeV, also derived from a single power law above 200 GeV, and hardened in identical way. And we can also perform the compare the AMS result with other experiments. So the red dots show the precision measurement from AMS in the rigidity from 0.5 GeV to the TeV in kinetic energy, and compare the different color from other experiments. So here the first plot shows the comparison for the neon, second shows the comparison from magnesium, and the last shows the comparison with silicon fluxes. So from all the plots, you can see that the AMS has very broad precision measurement on the flux. And more study could not only perform to look on the relative behavior between neon, magnesium, and silicon, and we can also to look at how the behavior with respect to the oxygen, so-called flux ratio to oxygen. And we can do the 3 ratios, neon to oxygens in the rigidity interval 2 GeV to 3 TeV, magnesium to oxygen, and silicon to oxygen. And to examine the rigidity dependence between the oxygen and the other higher charge elements, we can do the ratio, and can describe the ratios by the low energy 20 to 86.5 G by a single power law, and the high energy by another power law. So eventually that we observe the high energy, this kind of the power law index derived from the neon to oxygen is minus 0.046 plus minus 0.01. So this derived from zeros more than 4 sigma. It shows that the neon have a different rigidity dependence with respect to oxygen. And the same can be also seen from the magnesium to oxygen ratios and also silicon to oxygen ratios. And as explained before, that the spectrum neon, magnesium, oxygen to the neon, magnesium to silicon to oxygen low energy described by one power law, high energy divided by another power law, and we can get a special index for the low energy and the high energy. So at the high energy, that the ratio between the neon to oxygen, magnesium to oxygen, and the silicon to oxygen, all of them are consistent within the arrow. And we derive this index minus 0.046 plus minus 0.008. And this shows that the special index deviated from 0 by more than 5 sigma, and clearly shows that the neon, magnesium, silicon is a different class of primary cosmic rays than helium, carbon, oxygen. And this is the first observation from the AMS. So eventually, I will summarize the property of the primary cosmic ray nucleus from the helium to the silicons. So as I explained before, the helium, carbon, oxygen have analytical rigidity bandance above 60 GeV, all divided from single power law and hardening analytical way. We also observed that the neon, magnesium, and silicon also have a similar rigidity bandance for entire energy range, also divided from single power law and hardening analytical way. So this line is indicated that we try to use a double power law function to describe the ratio of the neon, carbon, oxygen, and also the fluxes of neon, magnesium, silicon. And eventually we derive this kind of gammas in the parameters is equivalent to the minus 0.046 plus minus 0.08, and that indicated in arrow band. It shows that the neon, magnesium, and helium, carbon, oxygen are different, and by more than 5 sigma. So eventually, a very important observation that we observe the neon, magnesium, silicon, and the helium, carbon, oxygen are two different classes of primary cosmic rays. So according to AMS measurement, we observe the very interesting phenomenon in cosmic rays that it like in primary cosmic ray, it has like a class structures. So light nuclear, helium, carbon, oxygen have a very similar behavior, and while that the neon, magnesium, silicon have another different behavior. So last, I would go to my summary. So the precision measurement of primary cosmic rays, neon, magnesium, silicons, fluxes from the 2.15 GeV to 3 TeV, based on 7 years of AMS data has been presented. And the neon and the magnesium spectrum have analytical rigidity dependence above 3.65 GeV, and the 3 spectrum have analytical rigidity dependence above 86.5 GeV, and deviated from a single power law above 200 GeV and hardening in analytical way. Unexpectedly, above 86.5 GeV, the rigidity dependence of neon, magnesium, and silicon spectrum is different from the rigidity dependence of primary cosmic ray helium, carbon, oxygen, and this significance is more than 5 sigma. And this shows that the neon, magnesium, silicon, and the helium, carbon, oxygen are two different classes of primary cosmic ray. And this important observation has been published in the paper as shown below, and also been chosen for the edit suggestion, also highlighted in the physics. And the MS precision result on other primary cosmic rays, this would also including iron measurement will come soon. So basically, we also have the measurement from high charge. And I promise that those results are also very interesting. So that's all my talk. So thank you for your attention.
Thank you. Let's go to questions.
So sorry, I have to show again, maybe. 1 moment.
So are there any, this difference that you showed, are there any explanations what that may be, or what is the take?
Yes. So for sure that there could be many explanations, but it could eventually go to the means the source of the stellar evolution. If the source has some spatial distribution, for instance, neo-magnesium will distribute differently with respect to helium, carbon, oxygen, it could reveal such a structure also. But anyhow, that more important, later we would also show our result on the other higher charge elements. And this would give a very important, eventually that important conclusion on this kind of the origin.
Questions? Okay, so let's thank our speakers again, all three of them. And we break again for half an hour, actually a bit less than half an hour. So let's start again exactly at 7 as scheduled. So see you a few minutes before. So we start on time, and we have 2 more talks left for the rest of the day. So thank you for now. Hi, everyone. Welcome back. Miguel, are you prepared?
Yes, I will try to share my screen.
Yes, please.
Okay. Can you see it?
Yes, we see that. Let's wait for a couple of minutes.
Perfect.
Okay, I think we can start the next session. And finally, we have two talks left. So our first speaker now is Miguel, who will talk about AMS. So Miguel, please.
Okay, thank you. So I am Miguel Ángel Velasco from CIEMAT, and I will present the anisotropy of elementary particle fluxes in primary cosmic rays with AMS. So let me start the talk with a brief motivation about the measurement of the anisotropy of cosmic rays with AMS. So the positron spectrum measured by AMS shows a significant excess above 25 GeV that is not consistent with only the secondary production of positrons. So the figure shows the latest positron flux measured by AMS as a function of the energy. And we observe that at low energies, the flux is consistent with the secondary production, namely the collisions of cosmic rays in the interstellar medium. But we observe a rise in the positron flux above 25 GeV and a drop-off, which is consistent with a source term. And the energy cutoff of this source term at about 800 GeV is established with a significance of more than 4 sigma. So this observation requires the inclusion of primary sources, whether from a particle physics or an astrophysical origin. And in the last case, the case of astrophysical point sources, they may induce some degree of anisotropy on the measured positron flux. On the other hand, we have also the electron spectrum, which in this case shows a significant excess above 42 GeV that is not consistent with lower energy trends. So the figure shows the latest electron flux as a function of the energy. And in this case, is well described in the entire energy range by the two power law contributions. And the most important thing is that contrary to the positrons, the electron flux does not have an energy cutoff below 1.9 TeV, which suggests that high energy electrons originate from different sources than positrons. And again, as before, astrophysical nearby sources of cosmic ray electrons may induce some degree of anisotropy on the measured electron flux. So regarding electrons and positrons, there will be more details of this on the upcoming talks by AMS people, and in particular in the plenary talk by Silly Wen on Monday. So, and last but not least, we have also the proton flux, as Mercedes presented before with the details. The proton flux shows a deviation from a single power law above 200 GeV. So this figure again shows the flux as a function of the rigidity, and we observe a progressive hardening of the flux at above 200 GeV. So in order to explain this observation, one should require, the model should require the modifications of cosmic ray transport models or the inclusion of local sources of high rigidity events. And again, a nearby source of cosmic ray protons may induce some degree of anisotropy in the high rigidity sample. So now let's move on to the analysis of the anisotropy. So the analysis of the anisotropy consists in the measurement of cosmic ray fluxes as a function of the arrival direction in a reference frame. And since the processes that we are interested in have a galactic origin, then galactic coordinates are suitable for this analysis. So galactic coordinates are an inertial reference frame, which has its origin on the sun, on the solar system. And there are three fundamental directions which are defined. The first one is the x-axis, or forward-backward direction, which goes from the sun towards the galactic center. We have also the z-axis, or north-south direction, which is perpendicular to the galactic plane. And finally, we have the y-axis, or east-west direction, which is opposed to the motion of the solar system around the galaxy, and finally completes the reference system. So as I said, we are interested in the directional dependence of the cosmic ray flux. And to quantify this, we have two contributions to the flux. The first contribution is the isotropic term, which is the phi 0. And we have also some small dependence on the direction, which is in our case is described in terms of an expansion in spherical harmonics, where the coefficients of the expansion are the so-called multipolar components in red. So at first order, this anisotropy is described by a dipole, and this dipole has an amplitude of delta, which is given by this formula, and describes essentially the asymmetry between the maximum and the minimum of the intensity of the flux. So this dipole can be projected onto the three fundamental axes mentioned before, giving rise to the three dipole components, the east-west, and the north-south, and the forward-backward, which are those components here and are related to the multipolar components in the expansion in this way. And they also allow to compute the dipole amplitude as the standard modulus of a vector. So it is also necessary to understand the sky coverage of the detector in a coordinate system of analysis. So let me go step by step and start looking at the coverage of the sky due to the geographical position of the ISS along the orbit. So taking into account the orbit, this coverage goes is a band that goes from minus 52 to plus 52 degrees, essentially, and regions closer to the poles are more exposed since the space station spends more time there. But we are interested in that direction, so we should take into account the field of view of the detector, which has some extension. And with this, the sky map in geographical coordinates, but looking at the direction, now it's almost fully covered. And if we take into account also that the z-axis of AMS is still 12 degrees with respect to the local zenith, then this explains the north-south asymmetry that we have in this map. And finally, if we perform the transformation to galactic coordinates, then we have this sky coverage like this, with essentially shows the very same features, but distort due to the rotation and the transformation of coordinates. So let me move on now to the details of the analysis, starting from the positron anisotropy. So the positrons are separated from protons with a selection based on a cut on the ECAL estimator and a template fit to the TRD response. So the figure shows how this template fit technique allows us to extract the positron signal from the data in a particular energy range. So with these positrons, with these selected events, we group them into 5 cumulative energy ranges above 16, 25, 40, 65, and 100 GeV. And in particular, for this analysis, we are using the event sample collected by AMS during the first 8.5 years of data, which amounts to 170,000 positrons in the first energy range. So these are the arrival directions of the positron events are compared to the expectation in the case that we have an isotropic flux in galactic coordinates. So this is illustrated in the figures that I am showing here in these maps. Here we have the arrival direction of positrons in the first energy range. So this is what we measure, and this is in the right, this is what we expect from the case of an isotropic flux. So in the case that we don't have any signal. Okay, so to compute this isotropic map, we need to understand, to have a very precise description and understanding of the detector efficiencies at different geographical locations. So the figure shows the positron TRD efficiency and its dependence as a function of the magnetic latitude. So for the first energy range. So it shows that it has a very small variation of about 2%. But if this small variation is not taken into account, this may induce an spurious signal if in the coordinate system of analysis. This can be observed also from the two-dimensional dependence of this efficiency in geographical coordinates and how this variation projects onto galactic coordinates, giving rise to a shape of a signal, a spurious signal, if this is not properly accounted in the isotropic map. So with these ingredients, one is able to compute the results of the dipole components east-west, north-south, and forward-backward for the 5 cumulative energy ranges. And this is what we have in these 3 figures. Just to mention that we also displayed the 1 and 2 sigma bands corresponding to the isotropic expectation, taking into account statistics and systematics. And as it can be observed, the results are consistent with isotropy in all the different energy ranges of dipole components. So this allows us to establish upper limits for each energy range, which are presented in the figure for the different energy ranges. And also we have the 1 and 2 sigma bands of isotropic expectation. In particular, for the first energy range, we found that the amplitude of the dipole anisotropy on positrons is found to be smaller than 1.7% at the 95% confidence interval. So, okay, so this is for positrons. Let's move on to electrons. So in addition to the sensitivity to nearby astrophysical sources, the measurement of the electron anisotropy provides a test of the systematics that are involved in the positron analysis. So again, for this electron anisotropy, we are using the event sample of 8.5 years collected by AMS. And in this case, we have a total number of 2.3 million of events of electron events in the first energy range. So as before, we have here the 3 dipole components in galactic coordinates with the very same format as before. And again, the results are consistent with isotropy in all the dipole components and energy ranges. And again, we are able to establish upper limits for the different energies ranges of the analysis. And in particular, for the first energy range, we found that the amplitude of the dipole anisotropy on electrons is below 0.37% of the 95% confidence interval. So regarding the positron anisotropy, we have performed analysis in the arrival direction of proton events collected by AMS in the first 8.5 years. And again, as before, we compare this distribution with the expectation for an isotropic flux in galactic coordinates. So in this case, we are using 9 cumulative rigidity ranges with rigidity ranging from 18, 30, 45, 80, 150, 200, 300, 500, and 1000 GeV. And we have here the arrival direction map of protons in the first rigidity range. In total, we have 140 million of protons. And this is compared with the isotropic expectation in the right panel. So to compute this isotropic map, again, we need to have a precise understanding of the detector efficiencies at the different geographical locations. In this case, we are showing, I am showing here the trigger efficiency, which is the most important for this analysis. and its variation as a function of the magnetic latitude. So we have a total amplitude of this variation of about 3%. And for this analysis, we are removing high geomagnetic latitudes. So with this, we are able to reduce the total amplitude of the corrections, of the efficiency corrections, then reducing the effects of the systematic with a small loss of statistics. And as before, this two-dimensional variation of the efficiencies, in particular in geographical coordinates, projects onto the galactic coordinate system, and it may induce some spurious signal if this effect is not accounted in the isotropic map. So with all of these ingredients, we are able to again to compute the three dipole components, the east-west, the north-south, and the forward-backward. We have here the results for the different rigidity ranges, as well as the 1 and 2 sigma bands. And the conclusion is that all the results are consistent with isotropy in all the dipole components and rigidity ranges. So again, we are able to establish upper limits for the different rigidity ranges of the analysis, which are shown in this figure, again with the 1 and 2 sigma bands. And in particular, for the we have an amplitude of the dipole anisotropy and protons for rigidities above 200 GeV, a total of 2.1 million of events. And this amplitude is found to be smaller than 0.35% at the 95% confidence interval. Okay, so this brings me to the end. So let me summarize the talk. So the precise measurements performed by AMS on the positron, electron, and proton fluxes show unexpected features that challenge the traditional paradigm of cosmic rays. And the study of the directionality of cosmic rays, namely the anisotropy, provides complementary information to the spectra and that may help to understand the origin of these features. So we have presented the measurement of the arrival direction, the anisotropy in arrival directions of cosmic ray electrons, positrons, and protons in galactic coordinates. And no deviation from isotropy has been observed. So we have established upper limits to the dipole amplitude. And finally, AMS will continue taking data until the end of the ISS operation, currently established in 2028. And by that time, positron statistics will allow us to reach the 1% level predicted by pulsar models. So that's it. So thank you.
Okay, thank you very much. Have time for questions. Any questions? So just to summarize, so you were saying, so you see a little bit of anisotropy for protons, but nothing for electrons, is that right?
Actually, we don't observe, we don't observe any deviation from isotropy. So all the results for positrons, electrons, and protons are consistent with isotropy.
Okay, also protons are consistent. Yeah. Okay.
Yeah. Yes.
We have a question by Peter Drabnicek. Peter, can you unmute and ask your question?
Yes, I would like to ask, I mean, what level of anisotropy actually you would need to address to actually to distinguish between particle origin of positrons and astrophysical origin of positrons? Maybe that's a naive question, but somehow if you can answer.
Yeah. It's a very interesting question. Actually, is this 1% level. Actually, there are many, as I said, there are many models to explain the positron excess. Some particle physics, let's say dark matter, or some astrophysical model, let's say pulsar models. So actually, the pulsars are at the level of the 1%. So for instance, there are two candidates, two of the most prominent candidates for this, which are Geming and MonoGem, and they're placed in the anti-galactic center. And if you add the contributions of them, they have a level of the 1%. So this is that's why I am mentioning here that by increasing the statistics in positrons, by the end of the mission, we should be able to reach that level and start to see if we observe some pulsar signal or not.
Okay, so that's why this analysis is so important for you, right?
Yes, yes, this is right.
Other questions? Okay, so let's thank our speaker again and move to the final speaker of the session. So, Tian.
Okay.
Okay, so our final speaker is Tian again on AMS. So please, you can start your talk.
So good afternoon. My name is Tian. I'm from the AMS collaboration, and my talk is precision measurement of the monthly boron carbon and oxygen fluxes in cosmic rays with alpha magnetic spectrometer on the International Space Station. So AMS is a large acceptance high energy magnetic spectrometer. It's able to perform precision measurement of particles in the GeV to TeV energy range. And AMS is operating on board the International Space Station since 2011, May 19th, and it has recorded more than 160 billion cosmic rays in about 9 years of operation, and AMS is expected to take data during the whole ISS lifetime. So what's the physical motivation to measure the monthly boron, carbon, oxygen fluxes? First, let's look at this figure. It shows the sunspot number as a function of the time. And you can see that there are many cycles, cycle 22, cycle 23, cycle 24, cycle 25 of the sun. And now we are currently in the cycle 24 and 5. And AMS, you can see that it's able to study the time evolution of the galactic cosmic ray during the both period of the maximum and the minimum of solar activities. The latest results from AMS shows discrepancies on the spectral behavior of proton and helium starting from February 2015. You can see that from the right figure that it shows the flux as function of the time. The blue are the protons, and the red are the heliums. So first, you can see that they have similar behavior. When you look into the ratio, the green one, you can see that there are some structures. They have first they are constant, semi-constant, and then they have a decrease with the time. This result is published in the Physical Letters 2018. So I want to know why, and is there a difference in the diffusion coefficient or because of the helium-3, helium-4 isotropic composition, or differences in the local interstellar spectrum? So the boron, carbon, oxygen are the closest, most abundant species. They can be used to understand the discrepancies on proton and helium, improving the knowledge of the nuclear propagation in the heliosphere. So this shows AMS subdetectors. We have TRD, transition radiation detector, to identify the electrons, positrons. And we have the time of flight to measure the charge and the velocity of the particle. And we have the silicon tracker, line layers. Layer 1 is on the top, layer 9 is on the bottom, and the others is in the magnetic ball and to measure. And we can use the silicon tracker to measure the charge and momentum. Of course, we have magnetic, and we have the echo, to measure the energy of the positrons, electrons, also the photons, and we have the rich ring image Cherenkov to provide precision measurement of the velocity. AMS is a precise detector. You can see from this. This is the chemical composition measured by AMS. This shows the abundance of all the elements. This axis is charge measured by the time of flight detector, and this axis shows charge measurement by the tracker. And you can see that we can measure the element from hydrogen to zinc, and we can AMS can identify element to element very well. And this talk is focused on the time evolution of the boron, carbon, and oxygen spectrum from about 2 GeV up to 60 GeV in intervals of 27 days, which is called the Bartel rotation. So let's look at the charge measurement with MS. It's for example, we are using use carbon as an example. First, this is the schematics, the picture of AMS and the carbon, the particle go into AMS in this direction from the up to the down, and you can see that here we have the tracker layer 1. It measures the charge is 6.2. It's carbon, and then in the TRD 5.6, and the upper time of flight 6, and in the inner tracker part 6, and the lower top 5.7, and the tracker layer 9 5.8, and echo 6. This means that this carbon goes through this detector without fragmentation interactions. So here, sometimes some particles pass through it. It may have some interaction. It will interaction with MS material to produce some other elements. For example, here shows oxygen from the top and interact here and become a carbon inside the inner tracker. So I just want to show you that we have a good control of these interactions. First, we look into the inner tracker, and we reconstruct the charge. Here, for example, we have the carbon, and then we look at the layer 1 to see the charge distribution. Here, let's say the first panel, the right panel, the first picture A, that it shows in the inner tracker there are carbon, and then at layer 1, you can see that most of them are carbon. Also, they have some nitrogen, oxygen, fluorine, and lithium. And in figure B, we shows for the oxygen, and that means that the inner tracker part, they are oxygens, and at layer 1, they have some, besides the oxygen, they have some other elements, fluorine and lithium, and also figure the C shows for boron. And for the flux measurement, the flux is defined as the number of the events divided the time, the exposure time, the effective acceptance, the trigger efficiency, and the beam width. The number of the events is corrected from beam to beam migration due to the track rigidity resolution, and the exposure time considers the duty cycle and the geomagnetic cutoff. And for the effective acceptance, it's estimated from the color and validated from data. The trick efficiency is estimated directly from data. So I give you the results of the flux. First, the left top panel, it shows the flux as a function of rigidity for carbon, and it's from May 2011 to April 2014. So let's first look at one color. Let's say the dark blue, and the dark blue shows the flux of 1 month, 1 bar rotation of May 2011. And as time goes by, you can see that the color is getting lighter and lighter, and light blue and in the bottom, the light blue shows the flux of the April 2014. So you can see that the flux is decreasing as time goes by, and in the low rigidity range. And of course, this is due to the solar modulation. We can clearly see this. And for the high rigidity range, they are it's almost the same. And the right top panel shows the flux as a function of rigidity. It's for carbon, and it's from April 2014 to November 2019. And the green color is the flux of April 2014, and the red is November 2019. That you can see that during this period, the flux is increasing, it's going bigger and bigger. So this is for carbon, and also on the bottom two panels shows the same period for the oxygen, May 2011 to May 2014, and the flux is going down. And for the other period, and the flux is going up. Also, this is the boron fluxes. So you can say we can come to the same conclusion: go down first, then going up. So this shows the relative variation of monthly fluxes with respect to the overall period average flux. That means first we do the average flux of all the battle rotations. Then we do the ratio. We pick up one battle rotation and to do the ratio. So first, the first panel shows the relevant variation of the ratio. In the first rigidity beam, that is around 2 GeV for the boron. That you can see, this is with time, the x-axis is time. So you can clearly see that there are some variations. So first it's going down, and then it's going up. So also for the carbon in the same rigidity beam, and for the oxygen in the same rigidity beam. And then for the lex rigidity beam, it's 2.15 to 2.40, and you can see that it's the orange color. And then the lex large rigidity beam higher, around the 3, the green points, and then the blue one around 4, and then okay, this is the blue one. Sorry, it's around 10, and then the purple one is around 30. So you can say that when the rigidity or the energy is going higher, the ratio is almost flat. It's almost have less variation. It's almost so I put the flux into one figure. Their flux. The left panel shows the flux for the carbon and oxygen. The dark blue is the carbon, and the light blue is the oxygen. And their flux as function of time, and in different rigidity beams, 2, 1, 2, 4, 10, and 30. And you can see that they have the similar behavior. And for the right panel, it shows the boron flux compared to the carbon flux. And the red is the boron, and the dark blue is the carbon in different rigidity beams, 2, 4, 10, 30, and you can see also they have the similar behavior. And then we'll look into the detail. First, this plot shows the carbon and oxygen fluxes. And in the first rigidity beam, around 2, as a function of time, you can see they are similar. And the ratio, it's we can see that it's constant as time goes by. It's constant. And for the next rigidity beam, we have the same conclusion, that the ratio is constant. And then for the larger one, 4 counts, so same conclusion. And the 10, so the behavior is similar. The ratio is constant. And 30, same conclusion. So that means for carbon and oxygen, the ratio is for all the rigidity beams, the ratio is constant with time. And then we do the same game for the boron and the carbon. And this here you can see the boron flux is the red one, and the carbon flux is the dark blue one. They have a similar behavior. And when we look into the ratio, you can see the ratio is not constant with time. At first, it's almost seems constant, and then it seems there is some decrease. It's not constant. And for the next rigidity beam, 2.15 to 2.40, and for the ratio, it's you have the same conclusion that first it's constant, then it have some decrease. And for the higher rigidity beams, around 4, the ratio is almost constant. And 10, around 10, okay, seems constant. And 30, constant. So that means for boron and carbon, the ratio for the lower rigidity beams, it's not constant with time. And for the higher rigidity beams, the ratio of boron to carbon is constant. And then we also do this for the boron to helium. And you can see the ratio as function of time for different rigidity beams. The first rigidity beam 2, and the same, the next rigidity beam, and 4, 10, and 30. You can see that for the first rigidity, around 2, and the fate is the line. You can see that it's not constant. There is a slope, and also for the next rigidity beam, we have the same conclusion. And then for the higher rigidity beams, so the ratio seems is constant. And then for the carbon, the ratio of carbon to helium, That's the same. So the conclusion is the same. At the low rigidity beams, the ratio is not constant, and while for the higher rigidity beams, the ratio is constant. And also for the oxygen, to the ratio of oxygen to helium, we have the same conclusions. So to my conclusions, the AMS measurements provide information on the propagation of charged particles in the helisphere. The boron, carbon, and oxygen time-dependent fluxes have a similar behavior. The ratio of carbon to oxygen are constant with time for all the rigidity beams from 1.2 GeV to 60 GeV. The ratio of boron to carbon is not constant at the low rigidity beams. The ratio of boron to helium, carbon to helium, and oxygen to helium are also presented. In the low rigidity beams, the ratio is not constant for the overall period from 2011 to 2019, where for the higher rigidity beams, the ratio is constant with time. Okay, that's all my presentation. Thank you.
Okay, thank you very much. We have time for questions. Question by Petr Dravnicek.
I'm just wondering if this is all related to solar activity, right? So do you have also some picture that relates these ratios and fluxes to the actual activity of the sun? And maybe another question, if you, maybe I wait for the answer.
Yes, it's of course due to the solar activity. Here you can see that we have a solar cycle, and we have the sunspots have the function of time, and here you can see that we have some maximum sunspot and the minimum sunspot. So this can cause the flux variation. You can see that due to the solar modulation, that the flux is changing.
Yeah. So right now we are in the solar minimum, right? So how the curves, how the graphs, plots you presented, how they will continue in the future, in let's say 2021, 2022, because you will still measure. So how these plots will change in the future?
Oh, here you can see that actually the maximum of the selectivity is around like 2014. That you can see that this it's like we get this it's decreased to here. We have a minimum, and then the flux is increasing. So in the future, now we are at the minimum of the sun activity. So we have the flux here. We have the very large. You can see that this flux is very large. Is increasing. So in the future, I think it may be just for me. I just think that it may be going down. The flux is in decrease, and then we have this cycle.
Okay. Yeah. Thanks a lot.
More questions? Okay, so let's thank our speaker again. And basically now we have time for discussion. We can also take a small break, but are people interested in continuing discussion in any of the topics presented so far? Any other questions, even for previous speakers, if they want to see some plots again?
Yes, I wanted to ask, I mean, it was mentioned that soon the AMS will publish new results about new topics like the fluxes of iron nuclei. So what is the approximative time scale for these new publications, if the AMS speakers can answer?
I have to say before this year.
Before the end of the year, did I get it correctly?
Should be in a few months.
Okay, yeah. Thanks.
We have a draft that we need to polish.
Mm-hmm.
Any other comments? People are tired. Okay, so I guess we can, if there are no more comments or questions or any of the talks, I think we can close the session. I just wanted to say that tomorrow there is a slight shift of the talks because a speaker canceled in the last moment. So the talks will be shifted accordingly, and the breaks will stay as they are. So hope you all join tomorrow for the next session of Astro-particle and Cosmology. So see you all tomorrow. Thank you all. Thank you all the speakers, and thank you all for participating.
Bye-bye.
Bye.
Thank you. Bye.